Okay, so we are live in YouTube, and well, you can start anytime you want.
Okay, I will start the recording.
I'm going to start right now.
Okay. Okay. Good afternoon, good evening, everybody. We are pleasure to start the afternoon in Brazil session on upper atmosphere and ionosphere. And during this afternoon, we're gonna have important names in the aeronomy field that were invited to give the talks. I would like to invite Professor Lorivaldo Lima from the Estadual da Paraíba to as chair of this session. Lorivaldo, go ahead.
Thanks, Igor. Good afternoon, everyone. And now I'm continuing the section about the upper atmosphere and the ionosphere. And we have an invited, now we have an invited lecturer. And for this, I am pleased to invite Friederike Lilienthal from Leipzig University in Germany. Friederike is a PhD in meteorology by Leipzig University, and he has been working with a three-dimensional model of the Earth atmosphere, simulating the dynamics of the middle and the upper atmosphere with focus on waves and tides. Currently is working as postdoctoral researcher at the Leipzig University. And now talk about modeling the middle atmosphere, high order solar tides and wave forcing mechanisms. Please, Friederike, you have about 40 minutes for your presentation. Thanks again for accept to talk about this theme here.
Yes, hello. Good afternoon, good evening to everybody. I'm very happy to give the talk here. Thank you for the invitation. Now let's try to start to share my screen. I hope this works. Can you see this?
Yes.
Yes. Yes, it's okay.
Okay, great. Yeah, okay, I'm going to talk about modeling the middle atmosphere, the high order solar tides and their forcing mechanisms. Yeah. So I will give first a little introduction to solar tides and motivation of high order tides. We'll also introduce the forcing mechanisms of tides. And then I want to introduce the model that we are using and some specifications about the tides and their forcing mechanisms in the model. And then I will come to the results section where I want to compare the amplitudes of the terdiurnal and the quarter-diurnal tides from different sources that we can separate in the model. I will also investigate the different forcing mechanisms and their interactions between each other. And finally, I will also show the impact of the tidal amplification on the mean flow. Yeah, of course, I will conclude with a small summary. Yeah, first I want to show a little bit about solar tides. For those who are not familiar with tides, you can imagine to be on a certain point at the planet Earth. And here, for example, it is the equator. latitude of 2.5 degrees north and yeah, near 0 degrees east. And you can see the total solar heating rates in the black line. And when it's night, of course, the heating rates are 0, and when it's day, they maximize and become larger. The exact number of the maximum is, of course, dependent from the latitude. And now we can decompose this daily circle of solar heating into its harmonics, and then we come out with the solar tides. The green line here is the so-called diurnal tide because it's 1 cycle per day. And then you have the semi-diurnal tide here in yellow. And this has, of course, 2 maxima a day. The terdiurnal tide in red, it has 3 maxima a day. And the quarter diurnal tide has 4 maxima a day. And these are the most important harmonics that are included in this black total line of solar heating rates. You can see already that the diurnal tide and also the semi-diurnal tide together make the largest part of the solar heating. But also the higher order tides like terdiurnal or quarter diurnal can be seen in the decomposition. Yeah. But why do we have a look at these high order tides? Why are they interesting? Usually they are less well investigated because they have smaller amplitudes. But the zonal mean, monthly mean amplitudes are smaller than the diurnal tide or semi-diurnal tide. But if we look very locally and occasional, then we can also see that both tides, high order tides, can even have comparable amplitudes to diurnal or semi-diurnal tide and also be comparable to the mean flow. Here you can see an example from publication of Jian et al. In 2009. They used meteor radar measurements above Maui. And this is, in this case, the meridional component of the terdiurnal 8-hour wave in 2002. And you can see that most of the time it is relatively small, the amplitudes, especially in the lower altitudes. But somewhere in the mesosphere, lower thermosphere, you can see some specific enhancements that can be relatively large. And this, of course, has some influence on the mean flow, on whatever you can see on the main dynamics in the middle atmosphere. And that's why we are interested in these tides. Similar amplification can be seen for the quarter diurnal tide. This is from Guharai et al. In 2018. They also used meteor radar measurements. And here you can see the zonal wind amplitude in 2005 as an example. And so you see here the day of the year on the x-axis, and on the y-axis you see the amplitude. And you can see that it is occasionally about 8, 9, 10 meters per second from time to time, depends on the specific location. Yeah, so also even the quarter diurnal tide can be large. But how are tides created? As I have already explained, that the solar heating rates are most important, and that it's about the daily cycle of solar heating rates. In Andrews et al., they define it as they are primarily forced by the diurnal variations of the heating due to absorption of solar ultraviolet radiation by atmospheric water vapor and ozone. This means that the semi-diurnal tide is mainly produced by ozone in the stratosphere, while the diurnal tide is mainly produced by water vapor in the troposphere. This is because the diurnal tide has to face some destructive interferences in the area of the ozone enhancement region, and that's why it is more productive in the water vapor in the troposphere. But there are other possible forcing mechanisms, not only for diurnal and semi-diurnal tide, but especially for high order tides. Of course, their relevance is under debate, so might be more or less relevant. So for example, there's latent heat release, which might, for example, come from clouds. There are nonlinear interactions, namely for the terdionytide. This is an interaction between the dionytide and the semidionytide. And for the quarter-dionytide, this is the interaction between dionytides and terdionytides, or an interaction between two different semidionytides. Additionally, you have interactions with gravity waves. So for example, Miyahara et al. Have shown that the terdionytide can be created by an interaction between the dionytide and gravity waves. Of course, there are further possible interactions with planetary waves, for example, during sudden stratospheric warmings, but they are not very well investigated yet. Yeah, and possibly there are even more possible mechanisms, but I don't want to go into detail with more. Yeah, so I want to introduce a little bit the model that we are using. It is a three-dimensional, nonlinear, mechanistic global circulation model. In the vertical domain, it starts at 1000 hectopascal. This is the lower boundary and extends up to about 160 kilometers as the log pressure height, where we take the scale height of 7 kilometers. The resolution of the model is 5 degrees in latitude, which is already seen, is shown here in the lower figure, and 2.5 for the terdionytide, and for the quarter-dionytide we have a different latitudinal resolution. It's 2.5 degrees. This is because the quarter-dionytide has a smaller meridional structure, and we want to resolve this structure explicitly. Yeah, the longitudes are always the same. They are 5.6 degrees for terdionyl and quarter-diurnal simulations. And in the vertical, we have also on log pressure height again, we have steps of 2.8 kilometers. In the lower 30 kilometers, the model is nudged by monthly mean zonal mean temperatures from era interim reanalysis. And here in the present simulations, we use ensemble simulations with monthly mean nudging of the years 2000 to 2010. So they are always 11 years averaged. And this an example is shown here in the zonal mean wind. This is such a typical climatology for January, where you have the westerly wind jet in the mesosphere in the northern hemisphere and the easterly jets in the southern hemisphere. And you have in these contour lines, these show the standard deviations with respect to these 11 different ensemble years. Yeah. Now we have different possible tidal sources. On the one hand, we have the solar forcing. We have a parameterization of the solar radiation for ozone, for water vapor, for oxygen, extreme ultraviolet radiation, and several more. And sorry, we have also nonlinear, the possibility of nonlinear interactions in our model, because on the one hand, we have the gravity waves, which are parameterized by an updated scheme. It's a combined scheme of a Lilienthal type scheme with multiple breaking levels included. And especially for the thermosphere, we also include the heat parameterization, because the Lilienthal parameterization does not account for those thermospheric effects. We also have the nonlinear terms because of the primitive prognostic equations. And so we can also resolve these nonlinear tidal interactions. What is not included in our model, any stationary or traveling planetary waves, they are explicitly excluded because we don't want to have further interactions. We want to see only the tidal interactions here. We do not have any orography or other tropospheric specific processes, so this is no complete Earth system model. It's only an atmospheric model. We do not include clouds, aerosols, or whatever. It is what is typical for the troposphere. And we also don't parameterize latent heat or any other non-zonal forcing. So the only thing we have are migrating tides, those that are sun synchronous. And yeah, so for example, the third ionotide only has a wave number of 3. There are no other wave numbers existent in the model, and the quarter ionotide only has a wave number of 4. Yeah, of course, we need a short validation of our model that the kind of reference amplitudes are comparable to observations. What you can see here are on the left hand, the model results for the third ionotide in the temperature, and on the right hand, so they're for December, and on the right side, the SABRE measurements from satellite, sounding of the atmosphere and broadband emission radiometry. These results were published by Pancheva in 2013, and you can see the latitudes on the x-axis and the height on the y-axis, where the height on the left figure starts at 80 kilometers, and on the right figure it starts at 70 kilometers, but the upper boundary is 110 in the SABRE data, where we can see a little bit further up in the model. And as you can see, these maxima are well reproduced. We have on the one hand this relatively large maximum in the lower southern latitudes. They are also seen in the model, and you have another smaller maximum in the lower northern latitudes, which are also seen in the model. There's in the satellite data somewhere near 50 degrees north, there seems to be another maximum, but cannot be shown in the satellite data, cannot be resolved. But in the model, you can see that somewhere near 50 degrees north, seems to be another maximum as well. So it fits well together, and we can work with these data to analyze forcing mechanisms. On the other hand, this was only December, so it may look a bit different in different months. And so we show here the annual cycle from January to December on the x-axis, and for different latitudes on the y-axis, at an altitude of 109 kilometers for the model, 110 kilometers for the satellite data again. And we can see that in general, the location of the maxima is well reproduced. So you have some maxima around the equator, always in the summer hemisphere. So it is slightly southward in January, December, and is slightly northward in June, July. And they maximize during the equinoxes in April and October. And in the middle latitudes, you see a certain enhancement in winter for both hemispheres. And this is also seen in the SABRE data. And so this fits well. On the other hand, we have one problem. The amplitudes in our model are much smaller than the observed amplitudes. So it's about a factor of 2 to 3 that we are missing here. But as we anyways only want to draw some qualitative conclusions, it's not necessary to reproduce the exact amplitudes here. Of course, it's something we can work on in further research and improve in the future. Yeah. Now we want to compare the amplitudes of the third ionotide and quarter ionotide from the different sources in our model. On the one hand, I've already explained that we have solar forcing, then we have the nonlinear tidal interactions, and we have gravity wave tide interactions. These are the 3 forcing mechanisms that we can divide in our model. And how can we do this? We have the tendency equations. Here is the example for the temperature. And we have nonlinear tidal interactions are the blue circles here. So everywhere where we have some multiplication between 3-dimensional variables, in this case, the U times T, V times T, and W times T, and the different components of the equation. We have the solar heating rates. They are parameterized, so this is only a very general term here. And on the other hand, we have the gravity wave heating that also comes from the parameterizations, the two from Linson and Diet. And we can separate the wave number 3 or the wave number 4 from these terms by applying a Fourier analysis in each time step of the model. So every time the equations are calculated, we can either only use the wave number 3 or 4, or we can remove the wave number 3 or 4, whatever we want to see in a certain model run. Here are the results of these runs. So on the one hand, we have on the upper left corner, we have the tide for the reference run, the one that I have already shown. So there's everything normal, nothing is removed. On the upper right corner, we have only solar forcing. So we have removed the wave number 3 or 4, or 3 in this case, because it's tide, for the nonlinear tidal interactions and for gravity wave tide interactions. In the lower left corner, we have a run where there are only nonlinear tidal interactions, so nothing solar, nothing gravity wave. And in the lower right corner, we have only gravity wave forcing. And what you can see already is that the reference run and this pure solar forcing run are relatively similar. There are some small differences, but they are similar. But you can also see that the run where we have only solar forcing can even have larger amplitudes at some points than the reference run. This is some interesting point that I want to analyze in more detail later on. For the nonlinear tidal interactions, we see that it is for January only important for the northern hemisphere, but amplitudes are relatively small. And for the pure gravity wave forcing, they are also relatively small, the amplitudes, but they are mainly important for the lower thermosphere, not really for the middle atmosphere. So we can conclude that the direct solar forcing is most important. Now we analyze the same for the quarter tide. It's again temperature amplitudes, and the runs are analog to those of the tide. So again, we have a reference run, a pure solar run, a pure nonlinear run, and a pure gravity wave tide interaction run. And again, we see that the solar amplitude is similar to that of the reference run. And also, again, we see that they are partly larger than that of the reference run. We also see that the nonlinear and gravity wave amplitudes are relatively small. They seem to play a minor role. They're not really important for the quarter tide. Yeah, so how can it happen that we have a larger pure solar tide than we have tides from all sources together? The hypothesis is that there are destructive interferences between different forcing mechanisms that can reduce the total amplitude, so they counteract in some way. This happens when the phase differences between the differently forced tidal tides are somewhere between 120 degrees and 240 degrees. If it's exactly 180 degrees, then they completely counteract and they can erase each other if they are of similar, of the same amplitude. We can prove this hypothesis by different simulations. So we have, on the one hand, the nonlinear tidal interactions. This simulation is called NLIN in this case. And we have another run where we have the solar tide and the gravity wave tide interactions together. This simulation is called no NLIN because it has only no nonlinear tidal interactions. We need to compare the phase relations between these two simulations, and then we can evaluate if there are destructive interferences, as I have stated. So what we see here are, it's a relatively complicated figure, but I will go through it very slowly so that you can follow. There are the colors on the one hand, the blue and the red colors. They show the amplitude differences between these different simulations. On the one hand, the run without nonlinear interactions, and on the other hand, the reference amplitudes. There's also a scaling factor included because we don't want to see the amplitudes exactly where they grow, but we want to see where the source regions of these tides are. And that's why we need to scale with a density, which is this exponential factor here. And the color red means that the amplitude increases even though we have removed the nonlinear forcing. So this is the interesting case, so to say. On the other hand, we have these hedged areas with these dots, and they show where we have destructive interferences, which means there we have a phase relation between 120 degrees and 240 degrees between the two different simulations, the pure nonlinear run and the run without nonlinear interactions. And this means and everywhere where the hedged areas and the red areas are fit together, the destructive phase relation seems to be the important point why the amplitudes are increasing. Yeah, here's an example for January. Of course, we have this for different months as well, but it looks similar in different months. And you can see that this relation fits very well together. There's a percentage in the lower left corner of the figure, and this percentage says how much of the red hedged area we have relative to the total hedged area. So how much of the area of all hedged points is in accordance with the red. And you can see that 82% is relatively high, so there's a good correspondence between these two effects. On the other hand, we have the same for quarter diurnal tides. And there we can also see that the red areas and the hedged areas fit well together. So it seems to be the case for the terdiurnal and the quarter diurnal tide together, that there are destructive interferences between the different forcing mechanisms. In this case, namely the nonlinear forcing mechanism and the solar forcing mechanism. They too counteract each other, and that's why we have higher amplitudes when we remove the nonlinear interaction term. Now we are interested in the impact on the mean flow. So what happens when we amplify this certain tide, for example, a solar tide or a pure nonlinear tide, and what is the influence on the mean flow? The method is that we increase a certain forcing of the terdiurnal or quarter diurnal tide in each time step. So, for example, we take the solar forcing, which is here shown on the left side for the terdiurnal tide. These are the heating rates, terdiurnal solar heating rates in absolute values, Kelvin per day. And now we increase these values by 5% everywhere in each model grid point. And after the whole model run, we see that as a monthly mean, we get about 1.05 of increase. So 5%, this corresponds to 5%, the green area here. So we get about the effect that we intended to have. We have some 5% increase of the forcing itself, the pure terdiurnal solar forcing. But what happens then with amplitudes, and what happens to, so amplitudes and zone wind and temperature and so on, and what happens to the mean flow, to mean temperature or mean zone wind? We show this here in a scatter plot, and on the left hand you have, on the left side you have the terdiurnal tide, on the right side you have the quarter diurnal tide. And the x-axis shows the enhancement of the forcing. We have here the solar forcing, and we enhance the solar forcing by a certain factor. So from no enhancement, which is 1.0, it's the actual value, up to the double of the original value, 2.0. And you see that the amplitudes, the zonal wind amplitudes of the third ionotide are increasing in the same way as we increase the forcing. It depends slightly from month to month, but it is about 1-to-1, the increase of the amplitudes and the increase of the forcing itself. We also put a regression line inside here, and you can see that for all months it's very close. No, this is not regression. Here it shows the slope, the S. You can see that the slope is close to 1, so it's about the same impact that we want to have. And for the quarter ionotide, this is similar. We have on the x-axis up to a doubling of the forcing, and we also have about a doubling of the amplitude in the zonal wind. And also the slopes are close to 1, so it's a very linear effect here. Then what happens to the zonal mean flow? Here we use a zonal mean zonal wind response. This is the change of the zonal wind averaged over the whole model domain. So for all latitudes and all altitudes. And for each factor of increase, or for each month, we apply a regression, and the regression coefficients are shown here in the legend. And you can see that they are also close to 1 for the third ionotide. And so we can see that it also has an almost linear effect. On the other hand, when we double the amplitude of the third ionotide, or this forcing of the third ionotide, the solar forcing, you can see a very weak effect in the zonal wind. There's only an increase of 0.2 meters per second on an average. This is relatively small, and we can almost neglect this effect. This is about the same for the quarter ionotide. The only difference here is that there are some more chaotic months. So especially in the northern summer, in June, July, August, the regression coefficients are very bad. So this is not yet solved why we have these chaotic behaviors in these months. Need some more research on that. And yeah, so we do the same with the nonlinear forcing. We again have a look at the zonal wind amplitude, the zonal wind amplitude of the third ionotide and of the quarter ionotide. Again, we increase the factor of the nonlinear forcing from 1.0 to 2.0, factor of 2. And for the third ionotide, we see that it's also about a linear effect and a very equal effect, like doubling of the forcing produces a doubling of the amplitude. But please note that this is relevant and also only with respect for the pure nonlinear run. So this is not in comparison to the reference amplitude, the total amplitude, where we have only small nonlinear contribution, but this is only in with respect to the pure nonlinear tide. So the pure nonlinear tide is increased by 100% when we increase the forcing by 100%. For the third ionotide, it is about similar, but again, we have some more chaotic months. This is again typical for the northern summer months. But it's about the same like for the third ionotide when we look at the winter months here. Again, we want to see if the zonal mean wind is somehow influenced. And what we get out of this is that, again, the regression coefficients are close to 1. It's about similar to the solar tide. But we see that the zonal mean wind is only weakly influenced by the nonlinear forcing. It's similar like for the solar forcing. And this is the same for quarter ionotide, and we have even a weaker influence on the zonal mean flow. Now the last one is the gravity wave forcing. If we increase the gravity wave forcing, we also have some linear effect for the third ionotide, but it's again relatively, it's again very linear for the increase, like an increase of 1.1. A factor of 1.1 produces a factor of 1.1 in the amplitudes. And this is similar for the quarter ionotide, but amplitudes can even be a bit more increased then. What about the zone mean wind for the gravity wave forcing? There we have again a relatively weak influence for both the third ionotide and the quarter ionotide. I don't want to go into detail with this anymore because it's very similar to the other forcings. And with this, I already come to my summary. We investigated the high order tides because they are so far relatively poorly investigated. We used a numerical model and we are able to separate the forcing mechanisms of the third ionotide and the quarter ionotide. As a result, we get that the direct solar excitation is the most important as for both tides, for the third ionotide and the quarter ionotide. Nonlinear interactions and gravity wave tide interactions are much weaker. We can see them, but they only play a role in certain seasons and altitudes, and they are much weaker than the solar forcing. The tides from different sources can counteract due to destructive phase relations. This is mainly the case between the solar forcing and the nonlinear forcing. We have done some additional model runs about the solar and gravity wave forcing, but there we have a much weaker influence. And last but not least, we investigated the zone mean wind and the impact of changed amplitudes on the zone mean wind, but we find that it's only weakly influenced by an increase of the tidal forcings. Yes, thank you so much for listening, and I'm looking forward to answer questions.
Thanks, Friederike. Excellent talk about the tides, solar tides, and the forcing. Question? Any question?
Well,
Oi.
thank you, Dr. Friederike, for the nice talk. It is really interesting results, really nice simulations. I would like to know if you can simulate the effects of terdiurnal and quaternion tides in the ionosphere using the NWRA model. Is it possible?
Well, at the moment, our upper boundary is at 160 kilometers in logarithmic pressure height. And it's possible, I guess it's possible to increase this upper boundary, but then we need to take more ionospheric effects into account, which are not resolved in the model yet. So at the moment, 160 kilometers is the upper boundary. And so only the lower thermosphere is covered here at the moment.
Okay.
Any question? Oh, okay, Igor.
I'm sorry.
Continue.
And I was curious about the interaction between the gravity waves and tides, because sometimes you have large amplitude and sometimes you have weak amplitudes associated with this interaction. And it depends on the season. And I don't understand very well why there is this seasonal dependence of the gravity waves and tide interaction. May you comment on it?
I guess it has several reasons. On the one hand, you have the tidal seasonal dependence. So, for example, in January, the third ionotide are relatively strong, and also different in different latitudes you have different maxima, so it depends very much on where you are on Earth. And on the other hand, also gravity waves have a seasonal cycle. So, you know, they are very important in the winter months, especially where they influence the mean flow, and also the mean flow in turn can change the propagation conditions of tides. And so it's most likely somewhere connection of all these different seasonal cycles that maximize the different waves. And yeah, then must be some interaction between these different seasonal dependencies.
Okay, thank you.
More question? Because my question, Igor, is about the importance the amplify depends on the season, and the other is about the mechanisms, the importance of the mechanisms. There are some season that the solar directly is more important than the nonlinear interaction for terdiurnal tide or quaterdiurnal tide.
Yeah, I'm not sure if I understood the question correctly, but yes, the solar excitation is by far the most important one. It seems to be that makes I don't know, like 95% or 99% even of this amplitude of the terdiurnal and quaterdiurnal tide, at least in our simulations. But as we have seen, the nonlinear and gravity wave forcing are important because of these destructive relations. And so they can reduce the amplitude, the total amplitude that we can see in our model. And that's why they are also important, not because of the strengths, just looking at them alone, but because of their interactions.
Thanks. Fabio. Fabio?
Well, we have to allow him to, let me find him. Okay.
Okay, thank you, Igor, for this for open my microphone, and thank you, Friederike, for this nice talk. In your presentation, you said that planetary waves are not included in this model, and my question is if this model is able to simulate planetary waves.
Yes, in general it is, but here I explicitly switched them off to avoid these interactions, additional interactions, because it might be possible that planetary waves and, for example, I don't know, you know, it's possible that diurnal tide and gravity waves together produce a terdiurnal tide, so why shouldn't it be possible that a planetary wave and a gravity wave together produce a terdiurnal tide as well? So I just wanted to make sure that these planetary waves are do not counteract in some way, but it is possible to switch them on. So usually in normal model runs, we include the stationary planetary waves of zonal wave number 1, 2, and 3. We explicitly force them and excite them at the lower boundary at 1000 hectopascals, and they are then calculated from the ERA interim data. Also, it is possible to excite additional traveling planetary waves. So you could, for example, include a 15-day wave or a 6-day wave or a quasi 2-day wave, Kelvin waves, whatever you like.
I see. Thank you. Thank you.
Okay. There are time for more questions. Any question more? It's no. In this case, thanks again, Friederike, and the yes, thanks.
Okay, thank you as well.
Okay, the next talk is about the statistical occurrence of mesospheric front observed in the Brazilian equatorial region. And I would like to invite Emanuel Barbosa de Carvalho.
Hi.
Emanuel?
Hi.
Okay. Emanuel Carvalho is a physics student in the Federal University of Campina Grande. It's correct? Is right?
Yeah.
Okay. Put your presentation and you have about 12 minutes.
Okay. Just to ask to remove this screen that is sharing right now.
Okay.
So I can share my screen.
Igor, help me.
Friederike, may you stop your screen?
Oh, is it already shared? Still shared?
Yeah.
Sorry.
Yeah.
I'm not actually sure how to. I thought it's already stopped. I don't know how to stop it because it seems it has stopped.
Okay.
Okay.
Okay, thank you.
Thanks. Thanks. It's okay, Emanuel?
Yeah.
Okay.
You already see my...
Okay, Emanuel, you have about 12 minutes.
Okay. So, good afternoon, everyone. I will be talking about statistical occurrence of mesospheric front observed in Brazilian equatorial region. And the objectives of this study was main to investigate the occurrence and preferential propagation direction and of mesospheric fronts observed over São João do Cariri. Besides the information around the main purpose of this study, information about the fronts, if the fronts presented wave trails or ripples while the front was passing was recollected too. And all the data used in this study is from an all-sky imager at São João do Cariri. So how was the study done? First, I would like to ask you to put the brightness of your screen at maximum so you can see clearly what I will try to show you at this video. So that is an example of one day of images that are working to, and we have here the local time, the date, and so we registered the date and time and removed from the data to the valid hours all the time that the sky was cloudy. So if this time was not considered while I was studying the other things. So, sorry, I am a little bit nervous. So we can see here. You can see here some ripples while this wave is passing. So this front, mesospheric front passing here seems to have a wave trail. So it all has been cataloged. Okay. So after that, the waves have been separated by month and season in which they occurred, and the seasons, looking at a simpler division, were being defined so that fronts occurred from January to March, having put at summer, April to June, at autumn, and so on. So what was found out by our study? First of all, through 25 months of all sky images, 144 fronts, mesospheric fronts, were detected. So 63.9% of the south fronts were followed by wave trails, which is an important data to classify mesospheric fronts, being one of the conditions to a mesospheric front be a mesospheric bore or a ducted wave. Ripples were observed while 19.3 of the fronts were passing through the images, which indicates dissipation of the fronts, may indicates dissipation of the fronts, and shows signs of local atmospheric instability. 13.9 of the fronts was not uniform as seen at the image. So some fronts were going bright to dark, and some of them were going dark to bright, and it's only 13.9% of these fronts, which may indicate, for example, that the observed phenomenon is or not a mesospheric wall, besides other observations that our study does not reach. So now we will see the main aims of this study. And the first of them is seasonality at mesospheric fronts phenomena occurrence. So as you can see in this first graph, there is not a clear seasonality since we have months where more fronts per hour. So here we have fronts per valid observation hours. That observation hours that are valid are the observation hours that is not that the sky is not cloudy. So we have months where more fronts per hour were observed, and it not seems to have a clear pattern. Well, as you can see, December here followed by May have more events per hour than all the other months. After those two, we have September and November that still get a high proportion of fronts per hour, higher than 0.1. And then these months where we have less events per hour, but still worth the mention. So February and October. But when you look the seasons, the mesospheric fronts per valid observation hours by season, we can see that this proportion is increased by through the year, mainly at autumn and spring, but with a more notable increasement at spring that reaches 0.1 fronts per hour. So it's important to remember that it's really early to do any categorical affirmation, and since we just have data from 2 years, and when other catalogations be done, we will finally be able to do a more accurate affirmation about that. It's also important to remember that this way of show data fix the problem created by 25 months analyzed. You can see here September 2018 to September 2020, so 25 months. Since this amount of months doesn't fix with a multiple of the amount of seasons in the year. Let's say, let's look at the other main aim of this study. So there was any preferential propagation direction of the south mesospheric waves. To determine that, we get all the waves and their direction by season, and finally through all the year, trying to see if they had or not and preferential propagation. And there is what we got starting by summer. So at summer, 12 fronts were detected. Of these 12 fronts, 5 were going to northeast, 2 were going to north, 2 to east, 2, and 2 to southeast. And no fronts were registered to any of these 3 directions here. So that is the, I forgot the word. So the stage of the summer, and now at autumn. At autumn, most of the registered fronts were going to north, 12 at total. Neither of the other directions had such an expressive amount of fronts compared to this amount, even though northeast and east had a good amount of fronts, 5 and 4 respectively. So they stage now to winter. At winter, the stage seems to change a little bit, since east and southeast have their amount significantly increased, while north and northeast stay don't register a significant change. South and southwest get a little increasement too, but that's not so relevant. Going to spring data. At spring, the amount of fronts going to east is still the same that in winter, but the amount to north is reduced. Okay, so when we look to the amount of fronts going to northeast, we see this huge increasement from 5 or 6 fronts in all the season. It just go to 24 fronts, and the amount to south had a little increasement too. Now, after see all the seasons one by one, we're going to see all years data. So we can see that thanks to spring data especially, the greater amount of waves is going to northeast, 40 waves. So showing us that this is the preferential propagation direction. But it's important to highlight that east and northeast here, no, east and north, sorry, are other 2 directions in which there is a great amount of fronts registered. So to finish this presentation, there are conclusions. The first of them, there is a seasonality in the occurrence of the fronts, in which most of them were observed during the spring. As you can remember, is the higher proportion of fronts per hour valid observation hour, and the observed preferred propagation direction of the mesospheric fronts was to northeast. So that's it. Thank you all.
Thanks, Emanuel, Carvalho. Any question? It's possible. 1 or 2 questions.
Lodivaldo, I would like to make a question.
Okay.
Simple question. Oh, Emanuel, could you go to the slide that you present the number of fronts observed according to the season?
So
I think it's okay, good. Go ahead, please. Next one. I go. Wow.
yes.
Okay. Yeah. Bar month of the year. No. Yeah. I would like to know if you have this behavior, because if I understand this figure, you in summer, for example, you take 2 years, right? But
Right.
what happened if you compare summer in 2018 and summer in 2019? Did you understand my question? I mean, I would like to see,
Yeah.
according to the season, but not collect in all of them in just one figure. I don't know if you could talk something about this.
Right now, I don't have this data apart one of the other. But if you want, I can separate those two and send by email. So
Okay, please do that. Okay.
okay.
Thank you.
Okay.
Any question? Okay, if not, thanks again, Emanuel Carvalho, for your talk. And now, after you close the presentation, because I need the.
Okay.
Okay, thanks. Okay, now we have invited talk, and I would like to invite Dr. Paulo Fagundes from Vale do Paraíba University in São José dos Campos, São Paulo. Fagundes is PhD in Space Science by the National Institute for Space Research, for INPE. He has experience in space physics and the Sun-Earth relationship, as well as upper atmosphere and the ionosphere. And now the talk is about the ionospheric disturbance and during strongest space weather. Paulo?
Okay. Are you listening?
Yes, we have about 25 minutes for
okay, I need to share I'm trying to share my screen.
Okay.
Can you see my presentation?
Not yet.
Not yet.
Okay. Can you see now?
Okay. Put in presentation mode.
Yeah, I'm trying to do
it. Yes.
Okay. Okay, I'm going to present today one of the strong events, space weather event in the last decade. This event was a solar flare that happened September 6, 2017. So in this presentation, you are using multi-instrument, multi-site observations. The solar activity region, ER 2673, emit 2 solar flares on September 6. The first one took place between 8:57 and 9:10 UT. It was a X 2.2 solar flare. This is how you classify the solar flare. Later I will show how you classify this. The second one was the strongest one. This event took place between 11:53 and the peak reached about midday. This was the strongest solar flare in the last decade. When you have a solar flares, in the ionosphere, you have sudden ionospheric disturbance, which means that the intensity of the electrojet increase and the F region electron density increase as well, leading to equatorialization anomaly intensification. So in this study, we are going to use a magnetometer network in Brazil and Africa, ionosound network in Brazil, Africa, and European. The VTEC inferred using GPS dual receivers in Brazil and Africa, and also some swarm satellite electron density diagrams. So the location of our instruments are in South America, Africa, and European sectors. So just to have one idea, how was the geomagnetic conditions during these days, you are going to present the geomagnetic index and also the interplanetary medium indices. I'm going to show the velocity and the proton density of solar wind, the interplanetary magnetic field PZ component, the X-ray flux, and UV flux between 5 and 7 September 2017. Here I have some indices. The DST index, I'm going to take the day 5 as a reference of white day, and the day 6 of September is when took place the 2 solar flares. This first red line indicates the X 2.2 solar flare. The second line indicates the X 0.92 solar flare. So the DST was relatively white. The solar index also was decreasing, but it was relatively white. The number of particles of the solar wind was around 3, 4 during both days. The interplanetary BZ electromagnetic field was around 0 during almost both days, which means that during both days that we are going to use, the day 5 as a white day and the day 6 as a disturbed day, they are quite on the quiet conditions, geomagnetic conditions. Here you have the 2 channels of the X-ray of this that we are observing by GOES satellite. So as you can see, during the solar flare, there is increase in the X-ray intensity. And here in the right, you have how you classify the solar flares. The strongest one you classify as X, then these two is strongest events. And this one, X9.3, was the strongest one in the last decade. So we are using two channels of X-rays to just to classify the solar flare. The first one is 0.1 to 0.8 nanometers, and the second one is 0.05 to 0.4 nanometers. So you are using this this X-ray just to show how intense was this solar flare, where these solar flares. The next figure shows that UV and EUV flux ranging from 1 to 100 nanometers from September to 5 to September 7. You can see also again here the signature of the solar flare X.2.2 and the signature of the solar flare X9.3 on September 6. So with these plots, you are showing how intense was the solar flare, how was the the geomagnetic conditions during these both events. So in these maps, I'm going to show how was the condition of the illuminating, non-illuminating area during both events, the X2.2 and the X9.3. This map is in the sea level. Of course, if you are going up to ionospheric height, this shadow area is a little bit different. The bright area also is a little bit different, but you have to take in account it just to see how was the situation of the shadow, illuminated, non-illuminated during both events. During the first event, the X2.2, the South America was during the night time. In fact, it was early morning during the first event. In the second event, the African and South America was illuminated. So then you can use this both events to study how is the response of the ionosphere in the Brazil and the Africa during this solar flare. Here I'm going to show just a picture how is the solar flare, one image to show during the solar flare what's the sun, what's happening in the sun. So we have a flux of the magnetic waves from the X-ray to visible to ultraviolet, semi-ultraviolet, to emanating from the sun. And these lights or magnetic waves reach the Earth 8 minutes after leaving the sun. So the first data that I'm going to show is the magnetometer data. In the upper panels, you have the magnetometer data from Brazil. And in the bottom panels, you have the magnetometer data from Africa. These dashed lines show the time when the solar flare 1, solar flare 2. I will call the X2.2 as solar flare 1, the X9.2 as solar flare 2. Though this is the condition of the magnetic field when you have the quiet day as a reference day, day 5. And the next day, the right panels show the conditions of the magnetic field during the solar flare day, this third day. You can see very clear during the solar flare, after the solar flare 1, the magnetic field is disturbed in the Brazilian region, and they also have some ripples in the African sector. So, and after the second one, that was the strongest one, the magnetic field increased a lot in both sectors. Also in the African sector, you can see some diminish as well. This station was from the mid-latitude, Hermanus, and the other one I don't remember because it's in Africa, so I don't remember the name. So what is important here, in both sector, Brazil and the Africa, after this, the solar flare one, you have some ripples, despite of Brazilian region is under the shadow area, which means that the early morning or the end of the night, the magnetic field is disturbed when you have solar flare. Of course, when you have the Brazil and the Africa are under the sunlight, the magnetic field is disturbed in both sectors. So, which means that probably the electrojet is very disturbing during this solar flare event. Now I'm going to show how was the VTEC in the Brazilian, African, European sectors during the solar flare. The first figure here, I'm going to show the VTEC in the west sector of the Brazilian sector, in the east sector of the Brazilian sector, because in Brazil we have a high density of the GPS receiver, so then it's possible to show data in the east and the west sectors. As you can see, after the solar flare one, the VTEC do not change in the west sector, not even the east sector. But after the second one, the X9.3, the VTEC increased a lot. The VTEC during the quiet day is the black line, and the red line is the disturbed time. So in the x-axis here you have time, and the y-axis have a VTEC. So we can see the red line is always above the black line here, indicating that you have a positive ionospheric disturbance. And the east sector, you have also an increase of the VTEC after the solar flares. What's interesting to call attention here, the east sector is more disturbed than the west sector. You do expect this because in the east sector was illuminated for more time than the west sector. The second figure is the African sector. So in the African sector, you do not have many GPS stations in the west sector, but only the east sector. So I'm going to show only the east sector of the African sector. You can see here some disturbance near the equatorial region, because we have deep latitude here, equatorial region, and low latitude. But at the mid latitude and beyond the crest, the equatorial anomaly crest, the VTEC do not change too much after the solar flare one. And after the solar flare 2, the strongest one, you have some disturbance in the VTEC that is represented here by the red line. These stations are mostly beyond the crest and the mid latitude. The disturbance is not so strong as we can see in the equatorial region, the low latitude. So this is a situation of the change that takes place in the African and the Brazilian sector after the solar flare. You have a very clear positive ionospheric disturbance at Brazilian sector, and in the African sector, you have ionospheric positive disturbance in the African sector, but in the mid altitude and beyond the crest, the VTEC do not change too much, and the values are comparable to quite day. Let's move to European sector. The European sector also have some, its figure is exactly the same here. The black is the reference day as a quiet day, and the red line is the disturbed day during the solar flares. So you have some disturbance after the first solar flare, positive ionospheric disturbance, and also the disturbance in the VTEC is larger after the second solar flare. So showing that you have very clear disturbances during the solar flare, included here in the European sectors. Now I'm going to show how is the ionospheric data using a ionosonde. The first plot here, I'm going to show how was the ionospheric conditions before and after the X2.2 solar flare 1 event. I'm showing here again the map, the sea level, and the X-ray, and the two channels of X-ray, just to remind you. In the Brazilian sector, as you can see here, you are under the shadow. So the ionospheric ionogram is very clear before the X2.2, and it also is clear after the X2.2. Here is 9 1/4. So both ionograms very clear, and in the African and the European sector, just before the solar flare, you can see the ionogram very clear, but after the solar flare, the ionogram is not clear because there are absorption of D and E region, so you cannot see the echoes from ionosonde because there is some blackout of the data. The data was absorbed by the E and D and E regions. This is quite well known behavior during the solar flare because there is an increase in the ionization in the D and E region, and all the frequency that you are transmitting from the ionosonde, these waves, radio waves, are absorbed in the D and E region. So this shows very clear that because you are on this shadow here, the Brazilian was not affected by the solar flare, at least when you see the ionosphere via ionosonde observations. So the next one is before the X93 and after the X93. As you can see, before there are some, you can see all the ionograms. But after, in the Brazilian sector, African sector, in the European sector, you cannot see any echoes from the ionosonde. This blackout took about 1.5 hours after the X9.3. The time duration was 1.5 hours. So during 1.5 hours, the ionosonde was not possible to see any echoes from the ionosonde. Now I'm going to show how was the equatorial ionization anomaly during this event. So again, the right panel is the quiet day as a reference day, day 5, and the right is the solar flare, and the left is quiet day. So you can see here using VTEC, it's possible to reconstruct the equatorial ionization anomaly and see that during the Brazilian east and the west, during the solar flare, there was an increasing of the equatorial ionization anomaly. And not only increase, the area of this increase the intensity, the area is larger, and the time duration also is larger than the quiet conditions. Then it's possible to say that the solar flare disturbed the equatorial ionization anomaly, and the AR become stronger, large area, and the lifetime was larger than the previous day. Also, you just to cross-check or analysis, you are going to use some satellite data from swarm data. So this is the Brazilian or South American sector. These first two maps show the quiet during the quiet day is during the solar flare day. Just during the first solar flare X 2.2, it's possible to notice that in the ionospheric heights there is some change, because the swarm satellite is around 500 kilometers height. So here you can see the path of the satellite and the electron density in this right figure. Then it's possible, when you compare the quiet and the disturbed day, note that there are at least at the 500 kilometers disturbance in the electron density increase a lot, and then there you have some disturbance. The bottom, the B figures, is during the quiet day, during the solar flare, during this strong event. It's possible not that the electron density increases almost the double of the, and you compare during the disturbed day and the quiet day. So you can say that both solar flare disturbed the ionosphere when you look at the ionosphere via satellite data, because we are going to see in a very high altitude, 500 kilometers, that maps that show the shadow and the bright area is not really correct, because that one is from the sea level. And how was the equatorialization anomaly in the African sector? So this top panel refers to September 5, the quiet day, and the bottom one is during the solar flare. Again, you can note that because the African sector was illuminating during the both events, the anomaly here, it's possible to see an increase as compared with the white day, and the most stronger disturbance took place during after the second solar flare. And again, the solar flare is more, the anomaly here is more intense have larger area, and the lifetime is also larger than the white day. This means that the equatorial ionization anomaly was very disturbed during these solar flare events. So now I'm going to show again for the African sector the swarm satellite data, the electron dense satellite data. This is the path of the satellite during these four paths. These two first figures refers to the first solar flare X 2.2. It's possible note that if you compare the first the quiet day and the disturbed day with solar flare X.2.2, the electron density increased by a factor of 4. Okay, but during the second solar flare, something different happened here. The ionosphere do not change too much the electron density. The only thing that's happened there during the quiet day, it's possible you see very clear the anomaly. The anomaly is characterized by two crests and one trough at the equatorial region, magnetic equatorial region. So here the equatorial anomaly is perfect. You can see both peaks and the trough. But during the solar flare, it's not possible to see the equatorial anomaly perfectly. You are proposing that during this event, what's happening is, since this event X9.3 took place during when the font effect that generated the equatorial ionization anomaly was stronger, and during this local time, what's happening is, as soon as the extra ionization was generated at this height, the font effect was moved into the low latitude, the extra, and this because this electron density became a little bit flat between from the south hemisphere to north hemisphere. So now I'm going to present my conclusions about using this magnetometer data, ionosonda data, GPS VTech techie, and also the swarm satellite electron density data. The conclusion is the horizontal component of the geomagnetic field in the South American and the African sectors. The X2.2 ripples are recorded in the agar component after the flare. This suggests that a minor disturbance in the H component of the geomagnetic field due to solar flare can be observed in the illuminated and non-illuminated sides of the Earth. The X9.3 H component just after the flare increased in the Brazilian and the African sector. The ionosonde observation. The X2.2 solar flare did not affect the ionosonde observation in the South America sector. The European and the African sector were disturbed, and there are some blackout about 45 minutes after this X2.2 solar flare. And after the X9.2 solar flare affected the ionosonde observation in the Brazilian, European, and the African sector for about 1.5 hours. The GPS VTech is disturbed in all latitudes for several hours. The VTech after the solar flare is around 20% larger in the west sector during the disturbed time, 41% larger in the east sector. Brazilian Eastern sector, 90% in the African sector, and 18% higher as compared with the quiet day. When you compare the quiet day and disturbed day, this is how much the VTEC increase in average, taking account all the stations that you have using this study. The equatorial normalization in South America and the African sector. During the sudden ionospheric disturbance, the IA is stronger, large, and has a longer lifetime when compared with the quiet day. The swarm satellite data are used to investigate the in situ latitudinal electron density around 500 kilometers. During the X2.2, the solar flare electron density doubled. During the X9.3, the solar flare electron density increased by a factor when you compare when the font effect is not present or still weak. What's happening is, during the early morning, the font effect is not strong, or at even is not developing in the early morning. So what's happening is the X9.3 solar flare in the American sector only increase the electron density, but in the African sector suggested the combination of solar flare and font effect changed the longitudinal profile of the in situ electron density. This is a result interesting because you do expect the solar flare take control of the ionosphere, but in fact what's happening is there is some competition between the solar flare, the extra electron density generated by solar flare, and the electrodynamics of the ionosphere in the low latitude and equatorial region. Okay, I will finish my presentation here. More details about this research you can find in Fagundes et al., Advanced Space Research 2020. Thank you for your attention.
Thanks again, Paulo. Good talk. Nice talk. Here we have a question sent by Eduardo Macho, and the question is, why the magnetometers in Africa show some station increasing values and the others decreasing after the second solar flare? And are they divided by latitudes or longitudes?
No, just because okay. Let me. Yeah. These two stations that decrease in fact, it's three stations here. Are these three stations TSU, Hermanos, HB? Okay. These stations are at mid-latitude.
Can you share the screen again, please?
I'm sorry. It's shared now?
Yes.
So, yeah, these stations here are located in the mid-latitude. It appears that only the equatorial and low latitude increase the magnetic field. The the mid-latitude decrease the magnetic field. The H component at least. Okay?
Okay. Any question? More? Okay, Paulo. If not, in this case, thanks again. Okay. Now,
Rafael is.
Rafael, have you considered plotting the deflection in the map to see the two-dimensional effects of the ionospheric currents?
Sorry, can you repeat again?
Have you considered plotting the deflection in the map to see the two-dimensional effects of the ionospheric currents? Magnetomic deflection.
I have not considered do this kind of plot, because I can explain what's happening with this plot. So why I do any extra calculation or difference of any.
Okay. Okay. Okay, Paulo, and thanks again. And now there are a break, and the continues 4 o'clock. It's correct, Igor?
Yes, yes.
Okay.
We'll come back at 4 p.m. Now we have a break of 20 minutes.
Okay, thanks.
Thank you a lot.
Bye-bye.
Ricardo, are you there? Ricardo,
Yes, Igor, I'm here.
You said that you
I tried to
talk to me.
Okay, but ok, Igor. A primeira palestrante não está aqui, por enquanto, né?
Deixa eu ver se ela entrou como
atendente.
Uhum. Tá aqui, eu vou permitir aqui.
Sharon vai estar aqui, ela. Good. Ok, beleza.
Deixa eu ver aqui se tem mais alguém faltando.
A Mila está aí. O Fabiano, vê o Fabiano.
A Fabiana ainda não entrou.
Fabiano
Você está na participante. A Fabiana ainda não entrou. Vou mandar uma mensagem para ela.
Bertoni está aí.
Tá.
Então, Inês também.
Okay, I'm going to start to record. João, are you there? No?
Yes, Igor, I'm here.
Yeah. May you start the record?
Okay. Okay, it's recording.
Okay. Hello, everybody. Good afternoon and good evening for the attendance. Let's start our last session of the day. And I'd like to invite Professor Ricardo Buriti from Universidade Federal de Campina Grande to serve as our chair of this session. Please,
Okay.
Ricardo.
Okay, good afternoon, good evening, and okay, let's start the last session of our atmosphere and the ionosphere. I would like to invite Dr. Sharon Vadas. Dr. Sharon Vadas is from research. She's from Northwest Research Associated in Boulder, Colorado, and with expertise in atmospheric gravity waves. I would like to invite her, but I don't know where. Dr. Sharon? Dr. Sharon Vadas? Okay.
Hello.
Hello. Hello.
Hello.
Hello. We are listening to you.
Hello.
Hello.
Hi, can you guys hear me?
Yes, we can hear you.
Okay, super. Let me see. I have to figure out how to share my screen.
Yes.
Hold on one second.
Okay, no problem.
Okay. So hold on a second. Sorry. Okay, I think I have the wrong. There it is. I'm a little confused at where the window is where I'm supposed to be sharing here. Shoot. Oh, wait, there it is. Okay.
Yeah, the screen.
Yes. Okay. And then I do share screen.
Yep.
And this one. Share.
Yes.
Okay.
Yeah, okay. We can see that.
Okay. Can you see my first slide?
No.
No?
I was.
So let's see. What am I doing wrong? What are you seeing right now?
A black screen.
A black screen. Holy cow.
We saw it before you put in the presentation mode.
Oh, I see. Okay. So you can see it now then?
Yes.
And it doesn't, so if I do, yikes. Okay, so if I do this, does it turn black?
Yes.
Oh,
Yeah,
all right.
no. Yeah,
Okay. Well, then I don't think I can do presentation mode. Actually, there's only one video. If you want, I can really quickly turn it into a PDF. Should I do that?
Someone is suggesting that you put first in the mode, presentation mode first, then you share. It's a suggestion.
Oh, I see. Yes.
Okay. Try.
But when I put it in presentation mode, I no longer see the Zoom thing. So here, I only have one video. So hold on a second.
Okay.
Just a second. Just made a. Okay, let's just try this instead. And okay, share screen. Okay. And then let's see, how do I make the PDF full screen? Presentation.
Okay.
Okay, yeah. All right. Okay.
Wonderful.
Can you see this?
Yes. It's okay now. So you have 45 minutes, okay?
Okay, sounds good. Okay. So in this talk, I'm going to be talking about, hold on one second. I'm just going to set my timer here before we do this so that I don't run over. That's the real problem with me. Okay. Hello, this is Sharon Vadas. I'm going to be talking about atmospheric gravity waves in the Earth's atmosphere. And I'm a researcher in Colorado, the United States. And just as a teaser, I want to point out, hopefully you can see this cursor, these rings in the TEC over the continental US on the 25th of March, 2015. And at the time, there was a superstorm occurring at the intersection of 4 states where the cursor is. And we analyzed this recently and found out that these rings are actually secondary, not primary gravity waves. So I think the feature of my presentations are going to be how do gravity waves and wave energy get from the lower atmosphere to the F region, and not just the F region, but also to Champ and Gochi satellite altitudes. So this is what I've been calling multi-step vertical coupling. And this is an example of it, which is that in this case, you're seeing waves that have not directly propagated from deep convection, but had an intermediate step where momentum was deposited and new set gravity waves called secondary gravity waves were radiated. Okay, so let's see. Okay, so I only have a few slides showing equations, so just bear with me. This is just in case anyone wants to look at this after. You know, if you're looking at waves in the air, and air can be described as a fluid, there are only 2 linear waves that can propagate in this air, not including tides and Kelvin waves and stuff like that. The 2 waves are acoustic waves, so sound waves, and atmospheric gravity waves. And the basic fluid equations, dry air fluid equations, which can describe the motion of this air, are shown here. These are the Navier-Stokes fluid equations. And the first one is conservation of momentum. V is the velocity. The second one is conservation of mass. Rho is the density. The third one is conservation of energy expressed in terms of derivatives of the temperature. And here you also see added in a body force, which can happen if you have waves dissipate and dump their momentum into the fluid. You also have molecular viscosity, which is very important in the thermosphere. And this as well, this is conductivity, heat conductivity. This is the damping in the thermosphere as well due to, yeah, this is damping in the thermosphere, energy damping. These equations describe the motions of drier air up to about 500 kilometers. So just a real quick, you can linearize these equations as seen here, and you substitute them in with wave solutions of this form, where h is the density scale height, and omega is the frequency, and k and l and m are the wave number. And the result is this, and this is the gravity wave dispersion relation. And it basically relates the frequency of a gravity wave to the wave numbers, the Coriolis parameter, the buoyancy, frequency n. And so this expression, as well as the Navier-Stokes equations, describe the propagation and dissipation of a gravity wave. Gravity waves are not like sound waves at all. They propagate perpendicular to their phase velocity. So in this tiny little sketch, here's the group velocity. The wave is going, say, northeast, but the phase velocity is actually going southeast. So so basically, acoustic waves, that's not true. The phase velocity and group velocities are aligned. And this is due to some special features of this wave as it propagates. And I'm not going to go through this. I'm just going to leave that there. Okay, so gravity waves can be, so this is an example which shows nicely what I want to illustrate, which is a gravity wave excitation from the geostrophic adjustment of the jet. And when we say the jet, we're talking about the background wind, and the jet is the place where the wind maximizes. So you have a jet usually in the stratosphere, the wintertime stratosphere. You have a jet near the tropopause. So here, this is an arbitrary axis, vertical, offset by whatever, 20, 30 kilometers, depending on which source you're talking about. And so this is Z and this is X. And here you have a local forcing. And this forcing, again, can be due to the adjustment of the jet. It can also be due to momentum deposition from gravity wave breaking, from many different things. And so basically what's happened here is that the background has sustained a horizontal acceleration. And this acceleration causes the background air to accelerate. And so the background air does not want to be in an accelerated state. It's okay having a mean velocity and or being at rest, but this is not a stable state. So what happens is the background fluid radiates waves in order to get back to a state of mean constant velocity, a state that's stable for it. And so here what you have is you have a radiation of gravity waves, and the waves, so when you look at these lines, say this red line here, the wave energy is actually going along the red line. But if you looked at a movie of this, the red line would be going down into the right. So if you looked at if you watched a movie of this, this red line would appear to move that way and go shallower and shallower in time. And that's again because the group velocity is perpendicular to the phase velocity. And then the other thing that to note, it's very important, is that gravity waves that propagate very close to the vertical, which is these guys, they have very high frequencies, or at least they have the highest frequencies of this source. And gravity waves that propagate close to the horizontal have very low frequencies. And the reason for that is down here. For a gravity wave, cosine of the angle is the intrinsic frequency over the buoyancy frequency. So that's it. And this is, of course, a windless expression with no dissipation. But this basically tells you that given an angle to the vertical, I can tell you what the intrinsic frequency of that wave is, because that's all it depends on. You know, it's not going to tell you what the horizontal or vertical wavelengths are, but it will tell you what the frequency is. And this is a special feature of gravity waves. So gravity waves that have very high frequencies, they propagate, say, if they can make it into the thermosphere, they propagate very close to the source. And gravity waves which have very low frequencies, say, very large scale waves, by the time they reach the F region, they're maybe thousands of kilometers from the source. And this is a feature, again, of their frequency. Okay, so therefore, I just want to point out gravity waves are quite different from sound waves. One cannot launch a gravity wave with a particular frequency, omega I, at any arbitrary angle that you want. The angle is determined by the frequency. So, and this point over here, wave dispersion causes initially localized gravity spectra to spread out spatially. So initially you excite this spectra here, and 12 hours later, in this case, the waves are spread out all over the place. So gravity wave spectra spread out due to not only their frequency, but also different vertical group velocities. Okay. So gravity waves are excited by a variety of sources. What are some of these sources and how can they be observed? And I'm going to be speaking about the ones that I'm interested in right now. So it's a little biased. So first I'm going to be talking about mountain waves. This is a very important wintertime source because in the wintertime, the jet usually is eastward and allows mountain waves to propagate up to 40, 50, 60, maybe even 70, 80 kilometers before they dissipate. Therefore, they can attain very large amplitudes. And when they break, they can deposit a lot of momentum into the fluid. So before we get into that, I just want to describe, probably people know what this is, but you have, in this case, an eastward wind flow going over a mountain, and then the air, because the gravitational force pulls the air back down, it sets up an oscillation, and these are called mountain waves. And here, when the air moves into a region where the temperature is lower, the moisture condenses out, and then you can see clouds. So you see these lenticular clouds at the tops of these mountain waves. And here's a picture of mountain waves east of New Zealand. So how can we observe mountain waves? This is a really pretty picture, I guess, taken from an airplane. Looks like it's lenticular clouds. And we can observe the effect that the mountain waves create. I imagine everyone has sat on a plane that landed near a mountain range on a windy day. The pilot might say, you know, we apologize for the turbulence. The turbulence is from breaking mountain waves. And this happens when the mountain wave amplitude gets too big. So here, this is a schematic sketch. Here you have a region where the mountain wave reaches a nonlinear phase and breaks and overturns. And that's, of course, bad when an airplane goes through. So an instability, so there's many different instabilities which can set in and you know, cause breaking. One of them is called the Kelvin-Helmholtz instability, and here you have overdense air over lighter air, and then an overturning occurs when the non-conventional amplitude gets close to 1. So you can see these images here of the Kelvin-Helmholtz instability. Usually you don't see these instabilities. These are rare events, but if you do, it's pretty unique. And once you have the overturning start, for the most part, the waves are usually wiped out, especially mountain waves. Sometimes they can just be damped down to a non-dimensional amplitude of 0.2 and grow again. It just depends on the background winds. So is gravity wave breaking similar to the breaking of an ocean wave? So first of all, I think I was just talking about mountain waves. A mountain wave is a special kind of gravity wave. So here when I refer to gravity wave breaking, I'm referring to gravity waves from all sources, including mountains. And is it similar to the breaking of an ocean wave? This is a nice picture. And I think that while there are many features that are common, this overturning look that you see in the simulations, here's some simulations of a breaking gravity wave. The answer is sort of, but not really. An ocean wave lies on the interface between two different fluids, ocean and air, but an internal gravity wave is internal to the fluid. There are no surfaces, so it breaks just because of the amplitude. So there are no surface effects. So how do we observe mountain waves in the stratosphere and mesosphere? Here's a beautiful way to observe mountain waves in the stratosphere is with the AIRS satellite. And here's an image from a paper, Alexander and Teitelbaum, showing the mountain waves over the southern Andes. And this is at an altitude of about 40 kilometers. And so the SABRE satellite observations go from the stratosphere all the way up to the mesosphere, sorry. So here, this is as a function of altitude. Here's the stratosphere, and here's the mesosphere. And for this particular mountain wave event, you can see these huge swings in the temperature. And then here the swings get smaller. And this is what's happening here is the mountain wave is saturating and reaching a critical level, and then it dissipates at about 80 kilometers. So this is pretty high for a mountain wave to get, but it can happen. And this is an important point down here in black. All mountain waves dissipate at or below the turbopause, which is the turbopause is at 107, and the turbopause separates the mesosphere from the thermosphere. And the reason that they all dissipate at or below the turbopause is because mountain waves have nearly zero horizontal phase speeds. And it's easy to show they cannot survive the molecular viscosity in the thermosphere. Okay, so what happens when mountain waves dissipate? Momentum and energy are transferred into the background fluid, and this accelerates and heats the fluid locally. These localized forcings and heating excite another set of gravity waves, and we call them secondary gravity waves. So there are several different kinds of secondary gravity waves. One kind, which is discussed in the literature, are small scale secondary gravity waves. These do not have concentric ring structure, but the secondary gravity waves that are excited by these forcings and heatings, they do have concentric structure, and they tend to have larger horizontal wavelengths. So here's an example here. This is a horizontal slice. So X and Y, so zonal meridional. This would be for a zonal force. And gravity waves would be going along the direction of the purple dotted lines. And you can see that basically for these secondary gravity waves excited by a body force, which is just an acceleration, you get the secondary gravity waves go in all directions except perpendicular to the force. And the other thing is, from that previous slide I showed you, the secondary gravity waves go up and down, and then backwards up, and then backwards down. So it's sort of like 4 headlight beams that come out, radiate out. And theory, this top right picture theory shows that excited secondary gravity waves have a fishbone structure and a time altitude plot. So this is a typical plot that you see from LIDAR observations. And this is a density scaled temperature. And you see here that, that you have this structure, which is it's anti-symmetric around the altitude where the body force is. And in this case, it's at 45 kilometers. And it can extend out for many hours depending on the duration of the body force. So this is theory. And then here you have, we have several cases of this where we've confirmed that the waves here, this is over McMurdo in Antarctica. And here we have pulled out the secondary gravity waves from Dr. Chu's LIDAR data. And you can see again the anti-symmetric phases of the waves. Somewhere around 43 kilometers is what we estimate the body force to have been. And the waves, these waves were going upwards, and these waves were going downward away from the body force. Okay, so let's see. So now I want to discuss, so what I want to discuss here is, so I think somehow one of my slides is missing. Oh no, shoot. Okay, maybe at the end, if I have time, I can go back and show you a slide which is missing. I don't know if I can do that right now. Sort of an important slide. I'm sorry about this. I'm just going to try to just pull it up really quick. It must have disappeared from my latest version. Okay. Darn, I don't know where it is. It's missing. Ah, okay. Well, okay. So let's see if I can find. Yeah, here it is. Okay. I hope everyone can see this slide. I'll just show this for a moment, and then I'll go on to back to the PDF. So what you see here is the results of a recent modeling study and published last year. And here you have a mountain wave event occurring over the southern Andes, a very strong mountain wave event. So this is at 20 kilometers. And then at 40 kilometers, you still have the mountain wave event, but the mountain waves have been evected downstream. And now they're concentrated at around 60 south. And then here at 90 kilometers, you have what looks like some circular structure. And these are the secondary gravity waves that have been excited where the mountain waves dissipated. And here, 100 kilometers, you still see some ring structure, but you see a lot of fine structure. That's from breaking secondary gravity waves. And then here at 130 kilometers, you have concentric rings. And no, these are not the secondary waves. These we showed to be tertiary gravity waves. And these tertiary gravity waves, here is 160 kilometer. And you can see that these tertiary waves propagate, in this case, northward up to the equator through Brazil, also northeastward over to Africa, and also some of them go southward and southeastward. And I think some of them go over the South Pole as well. So this is a stunning case. They're not always this stunning. They're not always this circular. Sometimes you see part of these rings, but this is a nice example to demonstrate this physical process which is occurring. Here's a schematic. Here you have your mountain waves being created, and they dissipate and they create local body forces. And body forces, we found they're more important than heatings, but there's also heatings and coolings as well. And these create secondary waves, and you see that these waves go up. And in this case, in this modeling study, we showed that the secondary waves dissipate from 80 to 130 kilometer altitude, and they excite very, very small amplitude tertiary waves, which of course grow in amplitude exponentially. And so by the time you get to the bottom side of the F region, they are the dominant thing. So remember I told you before that because mountain waves have close to zero phase speed, they cannot propagate into the thermosphere because they dissipate from molecular viscosity. So most of them break anyway in the stratosphere or lower mesosphere. And so this is a coupling mechanism that is based on solid, pure physics. There's nothing skeptical here, and momentum and energy are transferred from the wind flow over the mountains to tertiary waves that have large vertical wavelengths and usually medium scale horizontal wavelengths up to maybe a few hundred kilometers up to several thousand kilometers. And these propagate into and through the thermosphere, and they dissipate. It's a spectrum. So again, you have parts that dissipate at different altitudes, but some of them go through Gochi and Champ satellite altitudes, as well as the F region. So I call this multi-step vertical coupling, and it results in the transfer of momentum and energy to high altitudes. So I'm going to close this, because that was hopefully the only slide. Well, maybe I should just put it there. No, I should close it. All right. Okay, so hopefully I can go back here and go back to presentation mode. Okay. So hopefully everybody can still see this, and hopefully you'll object if you can't. So given what I just showed you on that previous slide, this slide will make more sense. So this is results that have come in over the last 6 years from Champ and Gochi data, which is that in the wintertime, there's a massive, what appears to be a gravity wave hotspot over the southern Andes. So here, this is the Gochi data at 250 kilometer altitude, and this is the Champ data at around 400 kilometers. And so using that model, which I just described on the previous page, Becker and Vadas, we just published a paper in JGR just a few months ago showing that we can reproduce this result. for the first time, a model has been able to reproduce this result of a gravity wave hotspot. This panel is at 200 kilometer altitude, and this panel is at 380 kilometer altitude. And these are for medium scale gravity waves. And it's very important, again, to emphasize that the gravity waves that make up these hotspots are tertiary and higher order gravity waves. So we believe we understand now the mysterious result of these waves. And again, these waves pass through the F region. So we're still working on how this could affect the F region. And this is work in progress. Okay, just want to show some quick slide of another study that I was recently involved in. This again was the Gochi satellite, and it was on a day when the Gochi satellite went over the southern Andes and over the Andes Mountains as well. And there was a big mountain wave event that was occurring at that time, and KP was less than 3, so it was geometrically quiet. And I can use fancy relations and polarization relations in order to extract out the gravity wave direction from the satellite direction. So if you want more information, you should look at this paper, but just want to show you the results. The results are that most of these Gochi gravity waves have lambda h, the horizontal wavelength. This is the real horizontal wavelength, not the along track horizontal wavelength. Medium scale, a few large scale, but more importantly, some of them have extremely large horizontal phase speeds. So the intrinsic horizontal phase speeds, most of them for this case are in excess of 300 meters per second. And you can show that, that a gravity wave cannot propagate faster than the sound speed in the environment that it's moving. So in the lower atmosphere, the sound speed is about 310 meters per second. A gravity wave cannot, intrinsic horizontal phase speed cannot be faster than that. In fact, it cannot be faster than 90% of the sound speed. So this is a big red flag that a lot of these Gochi gravity waves must be created in the thermosphere. And indeed, if you do reverse ray tracing of these waves, you only find that one of them could have been from the lower atmosphere. All of the other ones must have been created somewhere along these reverse ray trace lines. So I was inspired by a paper, Figueiredo, which I probably am mispronouncing, I apologize, but published a paper in 2018 showing waves in Brazil, and in the winter, they're mostly northward, and a good chunk of them, maybe half of them, have horizontal phase velocities that are larger than 300 meters per second, which indicates that a lot of these may also, again, or maybe even most, may again be created in the thermosphere. And perhaps these are tertiary or higher order gravity waves. So that's something I hopefully will be able to study with Cosmo. This is the inspiration again from that panel a few slides ago. These waves, the tertiary waves, they sweep in, going northward over Brazil. And this is typically because the polar night jet maximizes down here in the Drake Passage. And so that's where the mountain waves get to have the highest amplitude before breaking. And then that tends to be where the body forces are. They tend to be down here. And that's a function of the wind in the stratosphere, why they're down here. So that's why when the waves go through Brazil, these tertiary waves will tend to be going northward. I think it's consistent with this picture, with this data. Okay, so one last slide, I think, on mountain waves. This one is from a study quite a while ago, 2009, but we're looking at waves over Pfizer in Alaska, myself and Mike Nichols, and we noticed these waves that were going essentially southward, high frequencies, medium scales. So these would be called MSTIDs because this is measured in the electron density. and southward, and we thought, you know, what is the source? Because this was a geomagnetically quiet time. I think it was daytime measurements, if I remember right. And we trace these waves back to mountain wave breaking over the Brooks Range, which is shown here. It's a big, huge mountain range in northern Alaska. And at the time we called them secondary gravity waves. We didn't know about tertiary gravity waves, but probably these are actually tertiary gravity waves. They fit the profile of that. So, so again, these perturbations in the electron densities, if you're near a place with orographic generation of waves, these waves could be not from the lower atmosphere, not from the ground, but some intermediate step. Okay, so the second source of gravity waves I'm going to talk to today in my remaining 9 minutes are going to be gravity waves from thunderstorms. We call this deep convection. And so when you have, when the lower atmosphere is unstable, so essentially n squared is negative, the buoyancy frequency squared is negative, then if you push a little parcel of air up, it will keep going and going and going, and it won't come back down. Gravity won't pull it back down, and until it hits the tropopause, which in this case looks to be about 15 kilometers. And then when it hits the tropopause, it pushes the stratospheric air upwards by several kilometers, but the stratospheric air is stably stratified and n squared is greater than 0. So that air, after being pushed up, it comes back down, and then it might oscillate a few times before it relaxes. And that oscillation of the stratospheric air generates gravity waves. And here's an example of a storm generating gravity waves by Holton and Alexander. And you can also see, interestingly enough, that these gravity waves, at least some of them, are breaking at 70 kilometers as well. Okay, and this was the movie. It's too bad we can't see this, but this is another example of gravity waves from deep convection. And here you see the deep convection in GOES satellite images. These shows the cloud top temperatures. And wherever you have an overshooting plume, which I showed you on the previous page, those are extreme cold spots on the satellite. So if you just look at cloud top temperatures and identify the very cold spots, then you can identify these overshoot regions. And so this is a case where you had several deep convective storms occurring at the same time over the United States. Here's Colorado here. And this is measured in the OH air glow, which is about 90-kilometer altitude. And so the ring structure is fairly well preserved for the gravity waves that are excited by the deep convection. And that only tends to happen during the equinox periods, as GIUA showed in I think it was a 2009 publication. Okay. So gravity waves from deep convection have also been seen in the TEC. So this is a case from a tornado that occurred in Oklahoma and a Nushioka paper. And you can see the rings in the TEC. They've also been seen from typhoon as well as from just typical thunderstorms. And I just want to show you in the last remaining few minutes that I have, I want to discuss a recent case. So there's been many cases, but I want to discuss this case because, again, this case shows that this multi-step vertical coupling may also be important for F region gravity waves over regions of deep convection. So in this case, you had an enormous event occurring in the United States on 25-26 March 2015. There was hail, very strong winds. There was 8 tornadoes. There was it was a big mess. And what you saw a few hours later in the TEC were these beautiful ring structures. Sometimes they were almost 360 degrees, other times, just 180. And they were centered very, very, very close to where the GOES satellite indicated strong convective overshoot. So if you were just to say, well, look, it looks just like these gravity waves must have been excited by the deep convection because they're pretty much centered on the regions of deep convection. And you could stop right there and just write a paper, hey, look, we have these gravity waves from deep convection. But maybe that's not the whole story. And so what we did was we actually inferred the center, and then we followed the phase lines of the gravity waves as a function of radius to calculate their observed horizontal phase speeds, which you see here. Here's the C sub h horizontal phase speed. This is the radius. And here are the points. And what you can see is number one, the points are linear with radius. So this is two cases, the two cases, case one and case two. And so the fact that they're roughly linear with radius indicates that all of these gravity waves are from the same source, the same point source, or something that is similar to a point source, looks like a point source far away from it. And the other thing that you see is, okay, this case, the phase speeds are a little slower, although there are a few with phase speeds bigger than 300 meters per second. But in this case, almost all of the waves have phase speeds bigger than 300 meters per second. And some of them are a whopping, this one's 530 meters per second. This is huge. And these clearly cannot be from the lower atmosphere. Here it shows reverse ray tracing of these two cases. And all of the waves in this case, and most of the waves in the first case, cannot have been, cannot even propagate in the lower atmosphere, cannot have been from the lower atmosphere. I just want to point out real quickly, this does not take into account tunneling, which Chris Heel just showed last week at the AGU meeting, might allow some of these waves in this region to propagate in the lower atmosphere, and they could tunnel through. But these waves here, they could not tunnel through. Their phase speeds are just too huge. And the reverse ray tracing results also shows the inferred center of the ray tracing where the rays converge, and it's very close to the center of the TEC rings. And so that confirms that that these waves could have a thermospheric source and could have created the rings that we see in the TEC. And then the question is, well, why is the inferred center so close to the deep convective overshoot of the plumes? Is that possible? And you can look at this paper, but the answer is yes, because the highest frequency primary gravity waves from deep convection propagate very close to the vertical. So they have very high frequencies. Remember from the first few slides I showed, the highest frequency waves propagate very close to the vertical. Because they propagate very close to the vertical, they do not get very far horizontally by the time they dissipate at around 200 kilometer altitude. And so when they dissipate there, they're only 2 to 4 degrees away, so 200 to 400 kilometers away. And so it'd be very easy. So that's why the thermospheric body force that's created from the plume is only 2 to 4 degrees away from the plume. And that's why it would be easy to mistake the waves to be directly from deep convection. So I'm not saying that every time you see rings in the TEC, they're secondary waves, but I am saying in this case, we believe that this is true, that most these waves are most likely secondary waves. And as I show down here, this result has implications for the transfer of momentum and energy from the lower to the upper atmosphere via gravity waves and multi-step vertical coupling, even during deep convection. So we already showed a few slides back that this was true during the wintertime for orographic gravity waves, but it may also be true for deep convection as well in a more general sense. So in conclusion, I think I'm done here. Atmospheric gravity waves are created from wind flow over mountains, thunderstorms, hurricanes, typhoons. They are linear, they propagate upwards, and when they eventually break, they deposit their momentum and they affect, they cause the background fluid to re-radiate a new set of waves called secondary waves. When these secondary waves go up and dissipate, they deposit their momentum in the same way, either through breaking or molecular viscosity. And then the background fluid then it takes that acceleration and it re-excites a new set of waves called tertiary gravity waves, et cetera, et cetera. This thing can just go on ad infinitum. And the Southern Andes has one of the largest gravity wave hotspots in the thermosphere, according to Gochi and Champ data. The wintertime Southern Andes. And a recent modeling study confirms that these are tertiary or higher order gravity waves from mountain wave breaking. And then a recent study shows that the rings in the TEC in one case are secondary, not primary gravity waves. So to understand all of these waves in the thermosphere and in the F region ionosphere, it is likely that one must take into account this multi-step vertical coupling process. And the other thing I want to add is that given this, then maybe it's certainly true in the wintertime and possibly also in the summertime that you cannot account for the waves in the F region if you're using a model that only launches parameterized gravity waves from the lower atmosphere. So you must have a model that either resolves the gravity waves or that can launch secondary and higher order gravity waves in some manner. Thank you very much.
Okay, thank you very much to Dr. Sharon. Excellent presentation. I would like to open 2 questions. In advance, I have 2 here. And maybe one of them, I can open the microphone to Mesquita. I think I can do that. Let me check. Okay, allow to talk. Okay, I think Rafael Mesquita, you can talk.
Can you hear me?
Okay, it's okay.
Hi, Dr. Vadas. Wonderful presentation. Thank you very much. I have a couple of questions here for you. The first one is, how did you determine the altitude of the turbopause at approximately 107 kilometers for your 2019 paper from Sabre data? And the second one, it's what's the difference in the temperature signature of the gravity wave breaking and the Kelvin-Helmholtz instability breakdown into smaller scales waves?
Okay, wait. So the first question was about the 107 kilometer turbopause in the 2019 paper. And what was the second question?
What's the difference between what's the difference in the temperature signature, in the temperature profile of the gravity wave breaking and the Kelvin-Helmholtz instability breakdown into smaller scales?
Oh, okay. So I'm going to answer the second question first. That would be the expertise of Joe Wern or Dave Fritz in terms of all the different instabilities and how they look in the data. I work with models that parameterize some of that breaking at the lower ends. So again, I would refer you to these other studies. And to answer the first question, the turbopause at 107 kilometers, that was determined by rocket measurements decades ago. And that's where the rocket suddenly didn't get pushed around in all these directions from turbulence. So that, you know, they would go above 107 kilometers and it was smooth. And but recent results, especially by Lund and Fritz have shown that large amplitude gravity waves can break above 107 kilometers, but that they have the turbulence scale, like say at 140 kilometers, the turbulence scale is 5 to 10 kilometers. It's not 5 to 10 meters. So, and that's because of molecular viscosity is so strong. So in terms of the 2019 paper, I didn't actually use the results that the turbopause was at 107 kilometers. I didn't use that result to do that reverse ray tracing. What I did with that reverse ray tracing was I used, let's see, I believe I used HWN14 and MSIS for the temperature and the wind for the background. And then I used the standard molecular viscosity profile with the change that above 220 kilometers mu, the molecular viscosity is not constant anymore. And that's from a Vadas and Crowley 2017 paper where we noticed that there were waves at 300 kilometers that shouldn't have existed. And so we don't believe that those expressions hold above 220 kilometers for the molecular viscosity. So I didn't actually use anything about the turbopause in that reverse ray tracing. Does that answer your question?
Yes, it does. I was just curious to see how you have determined that. Thank you very much.
Oh, you're welcome.
Okay, I have another question of Brian's Amand. I will open the microphone for you, okay, Brian? So, Brian?
All right, good afternoon.
Hello.
Yeah, good afternoon.
Go ahead, Brian.
Now, can you hear me?
Yes.
All right. Thank you, Professor, for your presentation. It's really a nice one. In fact, this is the first time I'm really getting very nice understanding of gravitational gravity waves. I just wanted to know if the Kelvin-Helmholtz instability you talked about, if it causes the gravitational waves itself, or it is an effect associated with gravitational gravity waves. In other words, is it a signature for gravity waves or an effect within, or does it cause gravity waves? Another question I want to ask is that of what importance is the study of gravity waves to our everyday life? Sorry, I'm an amateur really. So I just want to know of what importance is the study of gravity waves to everyday lives. For instance, if you want to go to a funding agency and you're trying to convince them to fund a research in this area, what exactly should be told to this funding agency with respect to the importance of this study? Thank you.
Sure. So the first question was, well, all right, let me answer the second question first because I still remember that. So in the United States, the NASA has an enormous pile of satellites in the sky. And although I didn't talk about this, gravity waves can seed plasma bubbles and scintillation, which can actually disrupt the signals from the ground to the satellites. And NASA would love to be able to forecast when they're going to lose signals to and from their satellites. And of course, this is also true of GPS satellites, which are worldwide. And so I think for a US scientist, this is very easy to motivate, that forecasting F-region gravity waves is important in order for NASA to be able to forecast when they're going to have outages of communicating with their satellites, as well as when plasma bubbles are going to occur. And so that's the one I would say there. And then in terms of the first question, it had to do with KH instability, but now I've forgotten what the rest of the question was. I apologize. Can you repeat the first question?
Okay, I was talking about the Kelvin-Helmholtz instability. I wanted to know if it is a signature for the occurrence of GW, that's gravity waves, or does it give rise to gravity waves itself?
Well, so anytime you have an overdense fluid over a lighter fluid, this instability can happen. So for example, if you put, I think if you put water on top of oil, you'll have an overturning in that interface region. And I think they call this the Kelvin-Helmholtz instability. I may be wrong about that, but I think it's more general than gravity waves. I believe so, but you would have to go off and check that out.
All right, no problem. Thank you very much. It was a wonderful presentation. Thank you.
Okay.
Yeah,
okay, I have another question. It's very interesting because everybody that studied gravity waves has this doubt in his mind. The question came from Caio Martins, and the question is, how can we understand physically a wave that has phase velocity perpendicular to the group velocity? Okay, please, Sharon.
Well, so what happens in a sound wave is that the oscillation occurs back and forth along the direction of propagation, and so actually the atoms are just it's like a 1D plane. They're just going back and forth as they hit other atoms, and those atoms go in the same direction, and it's in the same direction. The gravity wave, a gravity wave, the atoms don't work that way. They don't move that way. They actually move in little ellipses, and the little ellipses cause the phase to go perpendicular to the direction of the energy is moving. I think the easiest thing to do would be to actually plot the streamlines and plot the way the atoms are moving, and then you'll be able to make sense of this. But just, from a straightforward perspective, a sound wave is really a 1D phenomena, and a gravity wave is a 2D phenomena, and it results in this perpendicular offset, and it's because the atoms and they're actually moving in little ellipses. So that's the quick answer.
Yeah. Is there any question? So I think you can stop here. Dr. Cheryl, thank you very much for your presentation. Okay.
Yep, thank you.
Thank you too. Okay, so let's continue this section. The next speaker is Fernando Bertoni. Okay, Fernando, just a second. I would like to introduce you, okay? Are you there, Fernando?
Yes. Good afternoon for everybody.
Okay, I can see your presentation, but I just to say to the people that you are a professor at the, I think I can say University State of Paraíba. I don't know if I can translate.
State University of Paraíba. We live at the same city, but don't see each other.
Yeah, so close so far.
So close so far. That's really
okay. Okay, Professor Fernando Bertoni works in the physics department, and he is a specialist in upper atmosphere. The title of presentation is Variability of Ionospheric Parameters of the Region Associated with Phenomena of Atmospheric Origin and Low Magnetic Latitude. So, Professor, you have 50 minutes, okay? So, go ahead.
Thank you. Hello, everybody. Thank you for attending my talk about the variability of ionospheric parameters of the region associated with phenomena of atmospheric origin in a low magnetic latitude station. This is actually the beginning of okay. This is a kind of start for this work because there is a lot of parameters to analyze, process, and instruments, different instruments. And in this specifically work, I have processed and analyzed some data from the COPEX campaign, which is also known as Conjugate Point Equatorial Experiment. It was led by the National Institute for Space Research in Brazil and several other institutions around the world, and the Air Army, a big staff participated, joined this campaign, and it is basically we have 3 locations, different locations in a semi-magnetic meridian nearby aligned. We have a station close to the magnetic equator and other 2 stations that are to the north of the magnetic equator and to the south of the magnetic equator. It's nice to observe that Brazil is, I think, one of the only countries that has this possibility. I have chosen a specific period of October from 7 to 12 in 2002 because we have simultaneous measurements of the coherent scatter radar at Ricamarca. Also, we have different instruments that register data in Cachimbo, Campo Grande, and Boa Vista. Besides, we have also, we had at that time, I think it's currently operating the São Luís station that is in another point around here, and Cachoeira Paulista that is in the southeastern part of the country. This is the location in a simplified map. And here we have some isolines of the magnetic anomaly, SAMA, South Atlantic Magnetic Anomaly. Of course, this region has more influence over this part of the country, but even in Cachimbo, we maybe have some influence of this. So we concentrated in the E region features. The E region has a usual behavior in which he forms just after the sun rises and almost disappears after the sunset. I have manually scaled the ionograms and took the parameters FOE, FOEP. This is the critical frequency of the region. This is predicted critical frequency. This is the minimum frequency of the region, minimum frequency of the F region, the true height of E region, and also the velocity of the true height of the E region. This is the instrument we have used in this work. This is the DPS-4. It works sweeping the frequencies, sorry. As you can see, for example, here we have the regular ionogram, well-behaved ionogram. Actually, the ionogram can show very weird features sometimes. Sometimes there is a total blocking of the sounding of the F region because a layer called sporadic E is formed, and sometimes the concentration of such layers are very high, and is in blanket the signal, absorbs the signal, and so we don't get echoes from the F region. This is the E region here. Sometimes also it's very difficult to take the correct profile, because we have sometimes just 2 points available. It's kind of hard work to do, and is very methodic, but it's necessary to ensure that the data don't have too much noise. This is a geomagnetic scenario of the period. In the left hand side, we have the DST for the October, the entire month. I used a different palette from the usual. This is for color blindness purposes. Some people don't see the green and red. So this is the specific period I have analyzed in this work. We see that the month itself have quite good activity through the whole month. The high phenomena, the most intense phenomena was in the beginning of the month, and we are just looking at this part here, right? So we start looking in day with some magnetic activity. The DST reaches the minus 120, basically, and it starts to recover. A little bump here, maybe it could be some substorm, and when it was recovering, as you can see, again, the DST exhibits this steep variation. But so the days, let's say 10, 11, and 12, they are quite And 7 and 8, I consider moderately to severely magnetic active. And these are the results. The first part is the variability of the parameters, the critical frequency, minimum frequency of a region, as well as the predicted value of the E frequency. And this is obtained by a model in a routine in the software, and the minimum frequency of the FU region. The blue is the predicted, so it's very well behaved. This is the regular behavior of the region. Sometimes we lack some points because of absorption processes that can occur during the soundings, you know. Sometimes we have to estimate some value based in the before and after ionograms, you know. This is the minimum frequency of the region, and this is the critical frequency of the region. Sometimes we see as a broadening of the layer, right? Sometimes it is condensed, more condensed, and it's the usual. This is very oscillating because of the absorptions of the signals. Going ahead, the days 10, 11, 12. Looking in this way, we just see some kind of usual behavior. It's not possible to see that much. And I decided to apply the wavelets transformation in these parameters, for example, FOE, and try to identify some periodicities, possible periodicities. In these days that we have more magnetic activity, we see some peak here of around 60 minutes, right? But there is a difference here. This kind of episodic, this part of 30 minutes, around 30 minutes periods is kind of episodic. This is for the days quieter days, right? So I can't identify very defined periodicities, but around some 80, 60, and 30 minutes, we can see some representation. This is the HME parameter, so the height of the true height of the E region, and we see some difference between the wavelets, the sets, and the periodicities are more or less the same, right? Sometimes they are shifted, but, and they show some bumps. For example, in the parameter of DHMEDT, we have this kind of bump. So the frequencies are spread over several periodicities, but around 60 minutes with some peak here, some shift, but it's likely that we might consider that these periodicities are similar to atmospheric gravity waves periodicities. The atmospheric gravity waves were just revised by Dr. Sharon Vadas. Very nice talk, actually. We know so far that nonlinear interactions maybe were responsible for the coupling with the higher atmosphere. And because the atmospheric gravity waves usually seems to break up 100 kilometers height. There are the coupling of lower and higher orders, as we have seen in the talk of Dr. Vadas. And so we have the primary, secondary, tertiary waves, and the dynamo regional electric fields are likely to be modulated because our high collision frequencies, the collisions between ion and neutron, have good values as compared with the geomagnetic field influence, right? And the oscillations are observed in ionization concentration measurements, for example, in ionograms or by the incoherent scatter radars that exhibit periods close to those of the atmospheric waves. So we may be facing the forces from low atmosphere, but as well, there are events that may reach the region coming from external origins. So we have to be careful with the analysis as well. And it's interesting that Sharon Vadas has shown that we may have a source in the thermosphere. The FEOE apparently presents oscillation periods, periodicities, or presents larger PSDs that may vary from day to day, but we have seen with some persistence, 30, 60 minutes and 8 minutes in some days. The HME presents some complexity in its behavior, but with similar periodicities as the FOE. And the HME DT exhibits prevalent 60 and 80 minutes periodicities, and not that much of the 30 minutes. Episodic characteristic of the AGWs are present and sometimes are persistent during some days. Apparently, the periodicities might have no influence of geomagnetic activity, but these are preliminary results and interpretations. More studies are necessary. Turbulent processes may have influence, concurrent processes of several natures, and we need to expand the analysis to a larger number of days of the COPEX experiment and to other stations of this experiment, as well as to look at data by other instruments and techniques. This is a work in progress already. The references, some references, and my acknowledgements to the State University of Paraíba and Department of Physics, the National Institute of Space Research, for my thanks for the collaborators, and congratulations to the initiative of promoting the ISP to the local and scientific organizing committees. Thank you, everybody. Thank you so much.
Okay, thank you, Professor Bertoni. And actually, we are 20 minutes later. And I think we can open to a maximum one question. Okay, I cannot see any question here. Okay, any question? Okay, the silence says no question. I would like to thank you, Professor. I would like to go to the next one. It's Fabiano Rodrigues. I would like to invite you to the next speak. Fabiano Rodrigues is an associate professor in the University of Texas in Dallas, and he's a specialist in ionosphere. By the way, Fabiano Rodrigues speaks Portuguese very well, so if some student wants to make the question in Portuguese, I think we can open an exception here. Fabiano, please, welcome.
Thank you. Can you hear me, Ricardo?
Yes, very well.
Okay, so let me try to share my screen here.
Yes.
Share, and you let me know if you can see it.
Okay. It's okay.
Can you see it?
Okay, no problem. Everything is okay.
All right. Thanks for inviting me to give this talk. So I thought about what I wanted to talk about today, and one of the things that I've been working on is related to experimental ionospheric studies using low-cost sensors. And what I wanted to say today is it's a collection of a few words about initial results and potential for new scientific collaboration and educational opportunities. So before I go into the talk itself, I wanted to say a few words related to the goal of this project and what made me pursue that type of study. Here in the US, I teach basic physics classes with large number of students, 250, 300 students in the class. I've been involved with undergrads, and there's quite a bit of demand for students trying to do work in space sciences, or they are just interested in space sciences and they wanted to have opportunity to work with it. So the initial goal for this project was to create the opportunities for hands-on experience in space sciences, but at the same time develop transferable skills to these students. What I mean by transferable skills is you would have the opportunity to work in space sciences, but you would learn something that would be applicable to a job position later on. And that's what students seem to be very interested these days. So having that in mind, some of the things that I needed to address in that project would be the interest of students in space sciences and technology. Students are also interested in computer programming, in physics, in the course, in the program that we have here at UT Dallas in the physics. Computer programming is not a mandatory course, meaning you can go through the physics course without taking one class in programming, but students wanted to learn about it. So this gives an opportunity for students to learn and practice. Also, recently, students have been interested in development boards. They wanted to work with sensors that are connected to Arduinos, Raspberry Pis, and other boards. So giving out this interest of students and some of my own interest in space sciences, we decided to do a study of feasibility of a low-cost, easy-to-build, easy-to-maintain Raspberry Pi-based ionospheric scintillation monitor. So ionospheric scintillation are fluctuations in the phase or amplitude of signals that are received by a receiver on the ground, and they are caused by perturbations in the density of the ionosphere. So we wanted to have a receiver that sits and basically measures the amplitude of the signal and can tell us whether or not the fluctuations are present. And then later on, we can evaluate whether or not those fluctuations were associated to some disturbance in the ionosphere. There are many instruments out there that allow us to do studies of the ionosphere, but there are very few of them that are low cost. An ionospheric sensor, ionospheric scintillation, for instance, if you wanted to buy one that is commercially available, a good one, it costs somewhere between $13,000 to $15,000. And that's probably one of the cheapest equipments that you can buy to do studies of the ionosphere. What we're working here is to use off-the-shelf equipment that you can build receivers that are only a few hundreds of dollars. A lot of people don't know this, but I have a very obscure paper when I was an undergrad, which was I used a commercial radio receiver to study propagation of HF waves. We detected the effects of solar flares, but I never, I published a couple papers on that and they never went back, and it was a low cost receiver, really easy to use, but I never had the time or the ability to go back to that. And now this gives me the opportunity to investigate a little bit more about low cost instruments. That being said, what I wanted to tell you today is I wanted to show you the design of what I call SynPy, which is this scintillation monitor that I developed with Alison in São José dos Campos and some of the friends that have helped me to do some observations. Then we're going to talk about the performance, how that compares with a commercial scintillation monitor. So now that I have this instrument, how does it compare with something that you buy that is really expensive? We don't expect to be as good as a commercial receiver, but how far we are off from those, that's what we wanted to take a look at. And then we're going to take a look at a short and long-term results. We placed that instrument in a site. We made new observations. I'm going to show you some examples. And then I'm going to tell you some of the things that I think that are nice and some of the things that I think that are not nice on the first version of the system that we developed. We have new versions that are being built. Those new versions are not as cheap, but they overcome a lot of the issues that we have with the first version. And then I'm going to talk about potential scientific collaboration. So one of the things that I wanted to tell you is this. We need to realize I'm from Brazil. There's a lot of people in this audience here that is from Brazil. We have an opportunity to do some really good stuff with students. If I have a scintillation monitor and I basically go with my students in Dallas and we start looking at a scintillation, we're going to be bored because we're not going to see scintillation. We're going to see scintillation maybe once a year, very weak, due to magnetic storms, or less than once a year. If you're in Brazil and you deploy a system like this, you're going to see scintillation almost every day on spread F season that runs from maybe August up to March, April. So it's a really interesting place for students to get engaged in this type of study, using low-cost sensors to study ionospheric irregularities and scintillation. So the next slide I have here is the design of the SynPy. So really, all you need today is to go to your online store and buy a GPS receiver like the one that I have on the left right here. This one in particular is the one that I thought that we used in the first version of SynPy. It's capable of measuring the signal from the L1 signal that is 1.5 gigahertz from the GPS. Has a serial data communication, meaning you can connect that device to a computer and transfer data from that receiver to a computer. Also, another thing that you need to have is the measurements need to be made at a high rate, maybe 10 hertz or more, so that you can see the fluctuations, you can measure the fluctuations in the signal. And the other thing that this receiver provides is the intensity of the signal. The downside is it only has a resolution of 1 dB. So you measure signals that are 30 dB, 31, 32, 33, every integer value, but you don't have in between. So it's really discretized between values of the, but we will see that that is not a major flaw. initially we thought that was going to be a problem, but it turns out not to be as much of a problem as we thought it would be. On the right-hand side, what you have is the Raspberry Pi, which is a single board computer that now you can connect that GPS receiver. That single board computer, what it's going to do is going to communicate with the GPS, is going to tell, hey, start making acquisitions. I want to know what is the value of the signal every 0.1 second. And I'm going to store that data into a hard drive, which is basically an SD card. And I'm going to store it, and I'm going to save that information for you to take a look later on. And those single board computers are really, really cheap. And one of the things is if you wanted to deploy and something breaks, if you had a full computer, it would be hard for you to send another computer. But if you have one of those and I am cooperating with somebody from Brazil, I can just send a Raspberry Pi, which is really cheap. And the communication between the two, between this Raspberry Pi and the GPS, is made by this cable USB to TTL adapter. So you basically, there's a protocol. I knew nothing about this, but there are out there, there's information about how you set up your code, your Python code, to make the communication between the Raspberry Pi and the GPS. I had undergrads that helped me to improve the code. And this is that part of the communication is that what is attractive to the students. It's a hands-on kind of experience. The Raspberry Pi also has internet. And that's going to become useful when you start making collection of data and you don't want to go there and grab the data manually. You want to just dump the data into a server, and that's what we do recently. If you feel attracted to this, there's a paper at the bottom here where Alison and I tell you exactly how we put the things together. And if you want, you can follow the instructions and try to do it yourself. And it's up out there. So this version, we basically tell people can build them their own receivers and do measurements of scintillation. Okay, moving forward now. So this is the first version, the prototype that we had built in the lab. On the left-hand side here, you have I hope you can see the pointer here. You can see the GPS connected to a case that has the Raspberry Pi and the cable. You can see the total cost is about $120. Includes everything, power supply, includes the antenna, a chip antenna, cable to the antenna, includes the cable that connects the Raspberry Pi to the GPS. $120. You have an ionospheric sensor, literally. Also, the way we set up now, we write a Python script, free. You can. Python is open source, so you can go and write your script and you collect data like universal time, date, SF, the satellite identifier number, the azimuth elevation of each satellite, and the intensity of the L1 signal, plus the latitude, longitude, and altitude that has been solved by the GPS. Once we built in the lab, we were happy with the data collection. We were bored that we didn't see any scintillation in Dallas. We basically, when we moved forward and we sent one receiver to Presidente Prudente in Brazil, where they install it, and they made collections for over a year. It never stopped. It started in January 2018. By December 2018, we decided to do the analysis of the data and had never had any problems with it for 1 year, almost every day. The only time we had issues is when the energy went out and somebody had to restart it, or we barely miss any day of observations. So, and the other thing is interesting about the Presidente Prudente is because you can see scintillation at various levels, so you can see how the system performed for different levels of scintillation. On top of that, there was a commercial receiver in there, so we placed the two receivers in parallel. So we could, after we collect the data, we could compare how SynPy scintillation measurements compare with the septentrial or the commercial receiver that was installed in parallel. When I mean parallel, I mean there is a signal that comes from the antenna, and the antenna splits into my receiver on the SynPy receiver and the septentrial receiver. So basically the two receivers have the same signal being fed to. This slide, what is showing you, it's a busy slide, but bear with me. All it's showing is data for each satellite for 1 day. each panel in here shows the data for one satellite at a time. So satellite 1, 2, 3, and so forth of the GPS constellation for February 11, 2018. In black, you have the intensity of the signal. In red, you have the elevation of the satellite. So when the satellite is overhead, you have an elevation of 90 degrees. So what you wanted to do now is you wanted to evaluate whether or not scintillation is occurring. The easiest way you can do that is to compute the standard deviation of the signal. The standard deviation of the signal is going to tell you a metric of how much the signal is fluctuating. Then you divide that standard deviation by the average value of the signal. So now you have a normalized metric of how much the signal fluctuates. If the metric is 0, it means there is no fluctuation. If the metric is 1, then it basically there's a lot of fluctuations in intense scintillation. So if you look at the bottom of this slide, I don't know if I'm going to try to use a pen in here. Right here, I don't know if you can see, there is a fluctuation here. You can also see the elevation doesn't change on this bottom panel in here. It's because the signal is not coming from a GPS satellite. It's coming from an S-band satellite that is just static on the sky, is not moving. So the elevation is always the same, the azimuth is always the same, and you're looking at the same direction in the sky. And you can see fluctuations between 0 and 3 UT, which corresponds to about 21 and 24 local time, where it's the time that you expect to see regularities over Brazil. That metric that I mentioned to you, which is the standard deviation of the signal normalized, is this blue line right here. Is this S4 that is indicated in here, sigma I divided by the average I is the intensity. That's how much scintillation is occurring. So you see these spikes going up. Every time the signal goes about, the S4 goes above 0.2, 0.3 is because you're having scintillation. So now you have an easy way to say whether or not scintillation is occurring by just looking at that number. And that's the number we evaluate. So this slide here basically tells, so now we have the sensor, it's sitting there, is measuring S4. So let's compare the S4 that we get with a S4 computed by a commercial receiver. This is what this plot here is telling you. In red is the S4 coming from the commercial receiver, and in blue is the S4 coming from the SynPy receiver. There are a few things that I wanted to point out. When the S4 is large, the SynPy and the commercial receiver, they agree. When the value is low, they don't seem to agree from time to time. And the reason is that cheap GPS receiver has a threshold value on the signal to noise ratio, meaning if it gets to larger than 52 dB hertz, it does not output larger than 52. It basically has a constant number of 52 dB hertz that is coming out. So if you see on the second panel here for the SVID7, you see a flat line. It means the signal was greater than 52. But the GPS has a threshold limit that says, I don't care if it's greater than 52, I'm going to output 52 for that long. So if you see any fluctuations around 55 or 56, you're not going to see because it's greater than 52 and you're only going to see that 52 output by the receiver. So you're not going to be able to compute the S4 and the S4 is going to come out as 0. That's not so bad because usually you have the signal when the elevation is great, when the elevation is high, then you have higher signal. But at that point, scintillations are not very strong. So we are missing basically weak scintillation, overhead weak scintillation. The other thing you can do is you can put a cable that is longer, that has a lower attenuation, so the signal never gets to 52. We didn't do that, but you could do that. The correlation between the commercial receiver and the SynPy is about 0.87 for all the data collected on a day. So it's a pretty good linear coefficient to have. And it indicates that we're doing good. We're not perfect, but we don't expect to be perfect given the price of a receiver, one costing $15,000 and the other one costing $150,000. So let's say that you wanted to do a study now, you have this receiver operating and you wanted to count how many times irregularities have been seen overhead or near you. You can do with the S4 coming from SynPy and this S4 coming from our receiver. And this is what you get for each month. The red one is from the commercial receiver. The blue one is from our receiver. Pretty much, we can capture most of the behavior that you can see with the commercial receiver, except that we miss some cases. And those cases are when the signal is really large. But we're doing pretty good. So these are the conclusions that I have for this. So we have the system, you can go and you can read the paper, and you can, if you wanted to build yourself, you can build. It's pretty fun to do it. You can get used to programming, you can get used to Raspberry Pi. But there are two other things that I wanted to talk to you about before I conclude. This is our newer version. I was so excited about this first version that I went ahead and I created a platform that measures scintillation. And instead of using GPS only, we used receivers that are a little bit more expensive, but are capable of making measurements of all the constellations: GPS, GLONASS, Galileo, SBAS, and Beidou. So this that you see here, it's a busy plot, you might not see very well, but it's telling you that I've been measuring on a given day over 100 satellites in the sky with my other receiver, the version 2 of the receiver, that it costs about $300, $400. So this measures so you're going to have a bunch of satellites in the sky. So this is the version 2.0. And now we have the version 3.0, and you can see you can see how things are looking different now. They're looking a little bit more professional, you know, on the side right here. So this is what SynPy number 3. I have a grad student, a really good grad student that is helping me. So now I'm basically that old kind of guy who just sits on the side and just tells the student to do things, and he's taking the lead on this. And basically, we built this, and this is capable of not only measuring scintillation on 2 frequencies, but also measuring TEC. So what I'm showing here are the results on top here, are relative TEC measurements made by this receiver in Ricamarca. And you can see in yellow here, plasma structures related to plasma bubbles. And when you have these structures in here, you can see the increasing S4 on the 2 frequencies, L1 and L2, and the scintillation associated with those. And everything makes sense. It makes sense because scintillations at the equator, where Ricamarca is, are very weak, and the bubbles are really not very deep like what you see in the equatorial anomaly. Finally, I cannot emphasize enough how this would be interesting to have in a program in Brazil, where you have students that wanted to learn about the hardware, the programming part, and they can do experiments. If you have a bunch of these receivers, you can do a bunch of different, I'll give an example. In Paraíba, you guys have airglow imagers. You can put an airglow imager and put a bunch of these receivers together, and you can look the correlation between the small scale structures in the sky versus the large scale structures that you have with your airglow imagers. You can do spaced receiver scintillation measurements. So now you can measure the velocity of bubbles with the spaced receivers. You can do TID detection and parameter estimation. There's a bunch of things that you can do that in other places you might not have the ability to do. So in Africa, you know, I missed Professor Rabdu's talk this morning, but I think would be an interesting place to put as well. It's really easy to maintain. Once you put it on, if you have internet, you forget about it. You will forget until I give you a call and say, oh, for some reason it's not working. But we have done this before and worked for like a year without me bothering people about running it again. So I'm going to stop here and I'll take your questions.
Okay, Fabiano, thank you very much. We have time for one question. Actually, we don't have time, but if someone has some question, please. Let me see if there is. Okay, so I suppose that when you spoke about low cost. If I understood very well, we can spend about $120 and have this kind of equipment.
That's correct. The first version that only measures GPS inflation, you can get as cheap as 120. If you save a few parts, it can be as cheap as $90. So there's ways to make it even cheaper.
Yeah, it's like extremely low cost.
Yeah, you know, it's compared to other things that we have, you know, it's really cheap.
Okay, questions? Yeah, Professor Fabiano, thank you very much for your presentation. So let's go to the other one, the next one. I would like to invite Marco Mila. Okay, Marco is.
Hi, good afternoon.
Yeah.
Can I share the screen?
Fabiano, please, could you unshare your presentation? Okay, thank you. Okay, Marco, sorry. Where are you?
Yes, yes, I'm sharing my screen.
Okay, let me introduce you, okay? So Mark Miller is from the Geophysical Institute of Peru. He's director of the Ricamarca Radio Observatory, and he's a specialist in the upper atmosphere and the ionosphere. Please, Mark, feel well. Thank you very much to attend this symposium.
Okay, thank you for inviting me to give this presentation. Can you see my screen?
Yes, it's okay. I can see the others, the next slides too at the same time, but it's up to you. Okay, that's okay, I think.
Oh, okay. Let me see if I can change this. Just a minute.
I think it's okay.
Yeah, it's okay?
It's okay.
Okay, then I continue. So today I'm going to make a short report on a few upgrades that we are conducting at the Ricamarca Radio Observatory in order to make the Ricamarca incoherent scatter radar more powerful, let's say. So this is first introduction about the observatory. As some of you know, the Ricamarca Radio Observatory is a research facility of the Geophysical Institute of Peru. It is supported by the National Science Foundation with an agreement with Cornell University, and it is dedicated to the observation and study of the equatorial ionosphere and upper atmosphere. It is located near the city of Lima in Peru, and we operate a variety of instruments: radars, ionosomes, magnetometers, GNS receivers, Fabry-Perot interferometers, airglow imagers, and others. And of course, we have our main instrument is one of the largest incoherent scatter radars in the world. And in the picture, you can see a photo of the Ricamarca radar, of the antenna of the Ricamarca radar. So let me first summarize some of the radar operations that we conducted during this pandemic situation. Some of you may know that Peru was in a strict quarantine since March 16 until June 30 this year. During that period, the observatory was closed, but we were able to operate the radar remotely in the Julia mode, which is a special mode dedicated to the observation of the equatorial irregularities. I mean, we can measure with this mode electrojet, 150 kilometer echoes, and spread F. In July, we were able to return to the observatory, but a small group of people returned, mainly the radar operations team, and we were able to restart operations in September. So as I mentioned, during this period, we were able to operate in the Julia mode, and after we returned to the observatory in July and August, we conduct full maintenance of the main Ricamarca antenna, transmitters, and the reception equipment. And then after that, in September, we restarted operations. We have run a few experiments since then. we have running our hybrid mode and high altitude drift mode in order to support the cosmic satellite mission. We have also run in several 2 occasions in the drifts plus fire plus imaging mode, which is a special mode that allows us to calculate electron densities, temperatures, and densities of the F region ionosphere. And we also have run in order to measure this, the radio noise generated by the sun when it passes through the Jicamarca antenna, and also other experiments during this period. This is just a summary, for instance, of the measurements that we conducted with the Julia in April. This is the first days in April, and you can see that we detected the spread F, equatorial spread F, every night, effectively every night during this season. So, well, that is now the current situation of the observatory. As I mentioned at the beginning, we are conducting some radar upgrades for continuous operation. So, what is the idea? What is the purpose here? We have received recently some funds from the National Science Foundation in order to implement 3 major upgrades, or 3 important upgrades at the observatory. First, in order to complete the electronic antenna beam switching system that we, in order to change the antenna position of the radar, or the antenna beam, in order to move the antenna beam. So some of you may know that in the past, in order to change the antenna beam, we had actually to go to the field and change the length of the cables of different parts of the antenna. And in that way, we were able to actually tilt the beam, the antenna beam. Well, now we have developed an electronic system that effectively changed the length of the cable, but do this automatically. And we are deploying this in the antenna field. First, it was implemented in the north and south quarters, and now with this support, we are going to implement it in the east and west quarter. That is one of the upgrades. The other upgrade is to replace tetrode-based transmitters that deliver 100 kilowatts of power. We call it the drivers. This is an intermediate stage of amplification that is needed in order to transmit with a high power transmitters at the observatory. This in the past, I mean, these transmitters, the ones that we currently have, are based on tubes, on tetrodes, but the new ones, the ones that we are acquiring, are going to be based on solid state technology. And the last one is the installation of a new antenna ground plane that was very deteriorated at the observatory, and this one will be able to, and with this one we are going to increase also the sensitivity of the antenna. So what is the goal with all these upgrades? The goal is to be able to implement a new Julia mode at the observatory in order to measure F region densities and drifts in a routine basis. As you know, with the Jicamarca incoherent scatter radar, well, we can measure densities and drifts and all that, but we cannot do this continuously. I mean, we typically run for about 1,000 hours during the year in these high power modes. And the main reason is that, well, because energy limitations, right? I mean, budget limitations in order to be able to operate at high power during those periods. With these transmitters that they are going to deliver only 100 kilowatts, we are going to be able to also measure drifts and densities continuously for about 4,000 hours every year. So that will increment significantly the amount of data that we can generate. And also the same type of experiments are going also to be suitable for the study of equatorial irregularities. I mean, at the same time, we are going to be able to measure the equatorial electrojet, the 150 kilometer echoes, and the spread F. So this is just a summary of the upgrades that we are conducting with the antenna beam switching. This is effectively, we are conducting some upgrades in the system that we developed, and currently we are, as I said, currently we are implementing the east and west quarters of the antenna, and we expect to have this ready by the end of the first semester next year. Also, in this plot, we are building at the observatory a new room for these solid state transmitters that they are going to be used in this new Julia mode that I described before. And they should be delivered actually in the first trimester of 2021. So we expected maybe to have it in February or March. And using these transmitters, we are going to be able to run routinely for 4,000 hours every year. So, and what are our expectations? What are we going to obtain with this type of radar modes that we are conducting with these new transmitters or drivers, as we call them? Let me show you the following slide. So this is a configuration of a new antenna configuration or an antenna configuration that we are going to use for this type of measurements. In this case, we are going to use the entire antenna in order to point perpendicular to the magnetic field. And this antenna is going to be, we are going to be able to actually measure drifts from the vertical direction. The parameters that we are going to use are effectively an APP of 1.5 thousand kilometers, and we are going to, in order, since we are using less power, we need to use a longer pulse in order to have more or less the same SNR approximately. And so we are going to use a pulse width of 75 kilometers. And we're using these two drivers, we expect to have about 120 kilowatts or maybe or even higher. And we are going to use also the full array on reception. These are an example of the type of measurements that we are going to be able to conduct. The first plot is just a plot of it's just an RTI map. I mean, it's the horizontal axis is time, the vertical axis is range, and in the colors is the intensity of the signal that we are going to measure. And in the second plot, we have a map of the vertical drifts that we can measure. As you can see, we are going to be able to reach, using this mode, more or less up to between 600 or 800 kilometers, more or less. Well, that will depend, of course, on the amount of density and on the period of the year. But more or less, that is the expectation we have, between 600 and 800 kilometers, and as a maximum range. And however, using this mode, we are going to be able to only measure the vertical drifts. So in order to be able to measure also the zonal drifts, we implemented, or we tested a second mode. In this case, we are using as some of you may know, the Hicamarca antenna is composed of two polarizations. So in this case, we're using one polarization to point slightly to the west and the other polarization slightly to the east in order to be able, combining both measurements, to measure the vertical and the zonal drifts. In this slide, we are summarizing the type of measurements and the system parameters that we implemented and compared with the standard modes using 1 megawatt of power. As you can see, our altitude coverage is not that far from the standard mode. Typically, with our standard mode, we were able to reach altitudes around 800 kilometers. Of course, the main difference is in the resolution. With these new modes that we are going to run, we are going to have a resolution of 75 kilometers effectively, while with the standard mode, because we were using coding, Barker tree code, we were able to actually have 15 kilometers of resolution, which is much better, of course, than the resolution that we are going to have, but we expect to obtain still good result with this new mode. Let me show the next plot. In this plot are showing a summary of the type of measurements that we were able to conduct testing this new mode using, for the vertical and zonal drifts. The second plot here corresponds to the vertical drift. The third plot corresponds to the zonal drift. As you can see with the vertical drifts, we can reach more or less up to between 600 and 800 kilometers. The bottom part of the region might be contaminated due to 150 kilometer echoes, but that is something that it can be managed since the drifts of the 150 kilometer echoes are pretty much the same as the drifts in the F region. So there will be a continuum there. And well, our altitude resolution, however, is going to be 75 kilometers, but for most applications, probably that is a good enough resolution. So just in order to conclude, let me mention that the Gigamarker radar has operated in Julia mode for about 3 months continuously during the quarantine period between April and June during this year. We returned to the observatory in July and restarted operations in high power mode since September. And our radar upgrades are currently in implementation. We expect to have the solid state transmitters delivered before March next year. And the antenna beam switching and the new antenna ground plane implemented should be deployed during the first semester of 2021. And with that, we are going to be able to implement this new radar mode that we call it the medium power mode. And that's it. Thank you for your attention.
Thank you, Milan. Thank you very much. Okay, we are open to questions. Okay. I have a question. If I follow you well, you said that this new improvement will make possible observation during about 4,000 hours per year. Is it correct?
Yeah, yes, that is correct.
Okay, so in this case, is there any period of the year that is the best for the observation in order to get the maximum of the instrument?
No, in general, we are going to be able to run throughout the year, and we are going to probably try to split the same amount of hours every 3 months. But there is no special period in which there is need to run. I mean, we are going to be able to measure drifts at any time, and that is something good because, for instance, when there is a CME warning or something similar, it used to take us many time to actually be able to prepare us in order to run for this type of experiments. But with these upgrades, we're going to be able to respond immediately to this type of situation and be able to conduct measurements. Most of the people is actually interested in the drifts and or the densities for their models. So we are going to be able to provide those type of measurements much more often than before.
Okay, thank you very much.
I have a question.
Please, Dr.
Yes. Marco, so you said that you will be able to run the radar in the Julia mode much more frequently, is that right? Because maybe in the past, the Julia mode was run only during daytime. Am I right or not?
No, the Julia mode runs also during daytime and nighttime. In daytime, we measure drifts. We measure the 150 kilometer echoes and the electrojet. And at night, we measure spread depth. But we were not able to actually measure F-region drifts. We were measuring the drifts from the 150 kilometer echoes. But with this mode, with this new mode, we are going to be able to measure drifts 24 hours. And we're going to be able to have a profile of drifts of the F region, and also for the densities. So this is the improvement, and it is going to be more information that we are going to be able to provide more information than before. And also we are going to measure the regularities at the same time. So that's the additional.
Okay, thank you.
Okay, let me see.
I have a little question, please.
Okay, go ahead.
Just one question. As comparing Julia and the incoherent scatter radar, have you already made some, how can I say, corroborating measurements? I mean, have you compared the measurements already for the same parameter, for example, drift, vertical and zonal drift?
Yes, I mean, with the Julia mode,
a kind of validation,
mode,
right? Yeah.
Yes, we have conducted some time ago validation that the drifts that we can measure with the Julia mode, that are drifts measured from the 150 kilometer region, they compare very well with the F region. There is a paper by Chow and Woodman. I don't remember exactly the year. I think it's 2004 maybe, or 2002. And they performed the comparison, actually, comparing the incoherent scatter measurements of drifts with the drifts that we can measure from the 150 kilometer echoes. And they found that they correlate very, very well. But still, as some of you know, in the drifts, there is a tilt as function of altitude. That was missing, of course, with the 150 kilometer measurements. With the new Julia mode, that we call it new, because this new mode is going to include also incoherent scatter measurements, we are going to be able to have profiles of the drifts as function of altitude, and then not only have the drifts from the 150 kilometer region, but also from the entire ionosphere. But the good thing, in addition, is that 150 kilometer echoes were only, I mean, they were only detected during daytime. So we were able to only measure in drifts during daytime. With this new mode, we are going to be able to measure drifts 24 hours.
Very nice. Very good. Congratulations. Thank you.
Thank you.
Okay, Fernando. We have another one, the last one. Please, Rafael, go ahead.
Hi. Sorry, I caught the presentation in the sort of in the middle, but I'm very excited to know that JRO is getting an upgrade. My questions are, who should I contact about a proposed study, and where should I go to see the JRO data product?
Okay, data products are in Madrigal. Let me show you the link. Here, that is the link for our database. So all the products are there in Madrigal, and of course you can contact me if you want to make any study with our measurements.
Thank you very much.
Okay, Mark Miller, thank you very much for your presentation. So let's pass to the next and last one of today. Dr. Inês Batista, please.
Thank
Dr.
you.
Inês from INPE, I'm so sorry, it's from INPE, and with expertise in ionosphere. Please.
Thank you, Ricardo. And I will try to share my screen here.
Yeah.
Let me see what I have. This one. Okay. Now I have to put in the presentation mode. Where can I do this? Okay, it's over here. Can you see my screen?
Yes, everything is okay.
Okay, good. First of all, thank you for those that are still here for this last presentation. And I would like to thanks Igor for inviting me for giving this talk in this symposium. I'm going to talk about the low latitude ionosphere response to the severe space weather events. I acknowledge my co-authors here from INPE and Universidad de Concepción, Chile. It's important to know, to talk first, that during the severe space weather events, the ionosphere at all latitudes can be drastically affected. I set the clock here, so I do not go until very late. There's magnetopause is compressed on the day side, magnetic storm take place. Auroras can occur at middle and even at low latitudes, and the whole ionosphere-thermosphere system is affected. Irregularities in the ionosphere can be intensified with drastic consequences, such as degradation of GNSS signal, with loss of lock and errors in the positioning. Also, electronic systems at satellites can become saturated or even seriously damaged. The lifetime of Earth's orbiting satellites can be reduced due to the increase of air drag. This means there is particle precipitation, temperature increase, atmosphere expands, so the air drag increases at the satellite orbit. And strong induced currents in electrical power transmission lines can overload the system, causing blackouts, as the one that occurred in Quebec, Canada during the March 13, 1989 event. Here, it's a simple, not a simple, it's in fact, it's fancy representation, but it's artistic representation of what happens during those solar events with coronal mass ejection that hits the magnetosphere and comes to the interior of the magnetosphere and affect the currents here and electric fields and circulation of winds and so on. During these events, the main things that will affect the ionosphere, drastically affects the ionosphere, are the prompt penetration electric fields, the disturbance dynamo electric fields, and the disturbance winds through the TIDs and the TADs, the traveling ionospheric disturbance and traveling atmospheric disturbance. Well, what happens is that those systems of current that it's affected during this disturbance, they can generate electric fields in the magnetosphere. And these electric fields, they can be transmitted promptly to the low latitudes. And the ioconvection at the high latitudes, they can accelerate the neutrals, leading to equatorial disturbance winds, while continuing energy input cause heating in the high latitude ionosphere-thermosphere system. And they come in the form of gravity waves, TIDs, or traveling atmospheric disturbance, including disturbance in thermospheric winds. The disturbance wind system, they produce longer lasting dynamo. That's the disturbed dynamo. They begin to dominate the low electrodynamics process with a few hours from the onset of the storm and continues for several hours well into and often beyond the storm recovery. In this presentation, we are going to talk mainly about the effect of the prompt penetration electric fields and the disturbed winds. The prompt penetration electric fields, they cause vertical drifts. And in these two plots here, we have examples of very, very intense disturbance, vertical electric fields that, eastward electric fields that caused vertical drifts around sunset in the Brazilian region. The first example here is that March 13, 1989 storm. The black continuous curve here is the quiet time around that period. And the two curves here are the results for Cachoeira Paulista and for Fortaleza. We can see that during the quiet time periods, the vertical drift was around 40 meters by second. And during this disturbed period, it came to more than 200 meters per second. It was a dramatic increase. Even more dramatic was the increase that occurred in this other event. It was the Halloween storm that occurred in the period between October 28 and 31st, and in which the vertical drift attained values higher than 700 meters per second. This one is equivalent to an electric field higher than 15 millivolts by meter. And the other one that was already very, very intense was around 5 millivolts per meter. Well, we are going to concentrate in this talk on this 31st October 23 magnetic storm event that was called the Halloween event. The chronology of this event was as following. On October 28, 2003, at 11:10, a major solar flare took place from the sunspot group directly in the line with the Earth. If you see this plot here, you can go that here on October 28th, you are going to see a huge solar flare here. And a high increase in the X-ray intensity. This event attained X17 on the astronomers' Richter-like scale of magnitude. Dr. Paulo Fagundes already talked about this scale in his presentation, so I do not have to explain it anymore. But it was a very, very intense X-ray event. Well, there was another very intense here on November. That was another magnetic storm, but we are going to concentrate on this one on the 29th of October. Following this, subsequently, a coronal mass ejection was observed to leave the sun in the direction of the Earth. And the magnitude of the solar eruption was so large that temporarily disabled the instruments on the NASA spacecraft AC instrument that was designed to observe such events. So the coronal mass ejection is showing here. And here is the snowstorm that saturated the instrument of the NASA. On 29 October at 6:11 UT, a major geomagnetic storm started in response to the solar event. The activity has reached the top of the geomagnetic scale of the measurements. So here it's the KP index, and it reached this value 9, so in October 29th. So this is the X-ray event again, showing the X-ray. And here we have the interplanetary index, showing that there was this shock here, the temperature, so the disturbance in the velocity of the wind, in the temperature, in the interplanetary magnetic field, the density, and the auroral index here. Well, I'm sorry, the auroral index is here, and here is the the DST, or the SIN age, showing that the storm, magnetic storm that started here. Well, such an intense event, solar event, of course, had a drastic response in the ionosphere. That this is what we are going to show in the next slides. Here we have the time versus height for the 3 stations in Brazil using ionosonde data: São Luís, Fortaleza, and Cachoeira Paulista. São Luís at that time was close to the magnetic equator. And here we have lines of same density. So the color scheme is here on the right. So we have that the plots, they are showing that for the height of the layer, the ionospheric layer, went up very drastically on the night, on the evening of the first night of the magnetic storm. This is the October, the time is here. So this is October 29, this is October 30, and October 31st. And the time in universal time is here. So around the pre-reversal enhancement in the equator, the height of the layer went up very drastically, and more drastically here in the following night, because the magnetic storm intensified. We have 2 subsequent storms. And in that period here was that the vertical drift attained values around 700 meters by second, according to that paper of Abdu. But in this talk, we are going to concentrate in another feature that was less explored in the literature. This is a different kind of plot where now we have densities in fact, we have frequency. The color code here is showing the frequency, but we know that the density is proportional to the square of the frequency. And if we look at the plots over Cachoeira Paulista, that it's here is equator, here is too close to the equator, and here is in the crest of the equatorial anomaly. It's in the crest of southern equatorial anomaly. And if you look at this time, the magnetic storm started around this time here. We have this line, white line here showing the beginning of the magnetic storm. And a few hours after the beginning of the magnetic storm, we have an increase, a significant increase in the density here at the crest of the equatorial ionization anomaly. Of course, this becomes more, we can see this more clearly in another type of plot. Now we are plotting only the FOF2, as I told you, the density is proportional to the square of FOF2. So the black line is the quiet day reference, and the red are the day of the storms. So we can see here that the frequency increased from 5 to almost 16. So it was 10, a factor of 10. If we, as the density is proportional to the square of this, so it was a very, very significant increase in the density. In a time, you see, this is 9 UT, so it's 6 local time. So this is not a time where we expect an increase in the density at these regions. As you see, the quiet period, the increase is very, very smooth. So in the other two stations, we have a kind of oscillation in this FOF2 parameter. And another interesting thing is that this was seen not only in Cachoeira Paulista. We are seeing this map here. This is the magnetic equator. This is Cachoeira Paulista. We have seen similar increases also in Tucumán, in Argentina, and Ascension Island in the Atlantic. All these three are close to the southern crest of the magnetic anomaly, and all these three locations, they saw this increase more pronounced in Cachoeira Paulista and Tucumán, and less pronounced in Ascension Island that was already in the daytime. You can see that Cachoeira Paulista was around 6 a.m. and Tucumán was 2 hours behind, so 4 a.m., around 4 a.m. Well, we can also say that after seeing this event in October 2003, we have looked for similar events in Cachoeira Paulista, and you found two similar events during disturbed periods in 24 November 2001, 31st March 2001, in which similar increases was observed in our station Cachoeira Paulista. This event was occurred in 2003. In 2006, we already tried some modeling of this event, but at that time, we only used a disturbed electric field. We did not introduce a disturbed wind, and we were not able to simulate the increase in Cachoeira Paulista. We were able to simulate more or less the behavior in Fortaleza and São Luís. We were able, I'm not showing here, we were able to simulate the variation in the height in the two low latitude stations as well, but the increase we were not able to simulate by modifying only the electric field. Well, after that, we decided to invest the effort in looking for a disturbance wind that could explain the kind of the situation that we observing here. Well, some authors have already made simulations use disturbed wind, but none of those models that they have used were able to explain the kind of observation that we had here in this very drastic event. The challenge that one faced to simulate the ionospheric response to disturbed events are the inputs that you need for those events. And for the main inputs that are most difficult to have are the vertical plasma drift or zonal electric fields and the disturbed winds. And I was very happy to hear from Dr. Mila's talk that the radar in Ricamarca is being upgraded, and we are going to have many results from drifts, the 24-hour drifts, because in our simulation, we use the supine-IMP model. The supine-IMP model solves the coupled time-dependent equations of continuity, momentum, and energy balance for 6 ions, the O+, the H+, helium+, NO2+, NO+, and O2 plus, and electrons along closed magnetic field lines. And this is the basic SUPIN. The SUPIN-IMP extended the calculations along the magnetic field lines from its original lower apex and base altitude limits from 150 to 130 kilometers down to 90 and 8 kilometers respectively, and adds the calculation of a seventh ion, the N+. As I already told, a challenge that we have to simulate the disturbed events is to have a good model for the vertical plasma drift or zonal electric fields and for the disturbed winds. So how did you approach this problem? Well, for the vertical plasma drift, first, this Manuel Bravo, he's the co-author of this research, this student, he is now in Chile, Concepcion, and he worked very hard on this. And first of all, in finding a good model for the vertical drift or the eastward electric field. Well, what's the better thing to have is measurement. And what are the measurements? Well, the incoherent scatter radar, if they are available, or if they are not available, drift deduced from magnetometer measurements following the procedure by Anderson, in which one uses measurements in two stations, one under the electrojet and one outside the electrojet, and by subtracting one of the other, we get the contribution of the electrojet. Another approach is the interplanetary electric field. The interplanetary electric field that can be determined following the methodology described in Kelly and Hetterer in 2008, and Hetterer and Keller 2010, in which the interplanetary electric field is calculated as the cross product between the velocity of the solar wind and the north-south component of the interplanetary magnetic field, but with varying efficiency. So there is a challenge here in determining the efficiency of this relation. Or the other one, but this is restricted in hours only to hours around sunset in the early evening hours. That is the drift calculated from the time variation of the F-layer height from ionosonde. And the other one, the Julia, Rickamarka, the Julia measurement. So, well, it's the Rickamarka radar operated in the Julia mode at 100 kilometers height, that we could derive the drifts from here. And this is the good news that we heard today from Marco, that this measurement will be with this upgrade of the radar. We are going to have a very good database for this. Because you see, for that event, we did not have the Rickamarka measurements. So what Manuel did in this, in his study, he chose some events for which we had measurements using the electric field was derived using all those techniques, for which there were measurements from the incoherent scatter radar, magnetometers, the interplanetary electric field deduced like that, the drift calculated from the ionosomes, and the Julia measurements. Well, then he compared the different techniques to see which one of them compared better with the incoherent scatter radar measurements that we are using as the pattern. So then he ran the supine INPI, used the different inputs, and compared the results with the ionosome observations at equatorial and low latitudes. Well, here is an example of these tests for determination of the electric fields. I'm not showing because we do not have much time, but I'm not showing. Britti, how much time do I have? So your microphone is off. How much time do I have?
Yeah, your presentation is now with 26 minutes.
Oh, I already exploded my time. Oh, I have to run. So this is a comparison between the electric field, deduced, not the electric field, the E-cross-B drift deduced from the interplanetary electric field and compared to the incoherent scatter radar. And those are the results after running the supine INPI for the density, for the height, and the FOF2 of the ionosphere. And we can see that the results using the Ricamarca and the incoherent scatter, the interplanetary electric field are very similar. The height compares very well, which we expect a better agreement between the heights rather than the densities, because here it's comparison for Ricamarca, it's an equatorial station. Well, so the challenge then for this October 2003 magnetic storm now was to use for this we use then the interplanetary electric field, the drift deduced from the interplanetary electric field, because we did not have the Ricamarca measurements. So this is the drift for that period, October 29, 2003, derived from the interplanetary electric field measurements. And for the winds, well, as I told you, for the winds, we have tested many models available in the literature by other authors, and none of them was capable of give good results. And we have see that we needed a waveform like that, propagated from north to south, in order to give that very huge enhancement in the density. So this is the waveform that we put this waveform in a background wind, that it's the HWM wind, that it's already inside the supine model. And it traveled, as the time passed, this waveform is traveling southwards. So we started in the northern hemisphere and is traveling southward. And with this, we run the supine INPI model, and the results are finally shown here. So that enhancement, the data here are the dots, and the blue is our simulation with this wind and the electric field. When we put only the electric field, we have this dotted line here. So we have, this is for Cachoeira Paulista, where the enhancement was most significant. This is for Fortaleza, we have this kind of waveform, and this is for São Luís. So what we finally, those are the simulation in terms of latitude versus altitude. And we can compare this with the observations that at 7 a.m., this is the same region here where we are going to observe the enhancement. At 7 a.m., we do not see enhancement here yet. This is between 7 and 8. Between 8 and 9, we already start to observe enhancement here. And here, the density is increasing. And between 8 and 9, we do have a very high increase here. That was we are observing here already. And between 9 and 10, we now, the enhancement are moving to the north and to the south, that what we are seeing here. So it seems that that kind of electric field and wind was very efficient to simulate this very drastic event in the early morning ionosphere in the Brazilian region. So my final remarks are here. I will stop because my time already. I'm past the time already. Thank you.
Okay, thank you very much, Inês. Okay, we are open to question. Fast question. Okay, please. Thank you very much for.
Inês.
Okay.
Yeah.
Have you used? Sorry, the model of wind that you used, what was? How have you modeled the wind? I haven't.
We have a wave front like this. This is a wave front for in São Luís, and it's propagating from north to south. It's propagating from, first it passed from São Luís, after to Fortaleza, and later to Cachoeira Paulista. And we have superposed this to the regular HWM model that it's already embedded in the SUPIN-INPE model. So we put a wave front that it's a kind of TAD, the traveling atmospheric disturbance. We put a traveling atmospheric disturbance propagating from north to south in the background wind that was already there in the model. So this traveling atmospheric disturbance was able to explain that that behavior of the electron density that was observed in our data.
I see.
Did I answer?
Yeah, you took the different profiles at different latitudes for the wind, right? You see? The blue has Cachoeira has a peak.
Yeah, it's traveling with time. It's traveling with time.
I understand that.
Yeah, it passed first over São Luís, later over Fortaleza, because it's traveling from north to south.
I see. Nice.
Okay.
Interesting. Okay, thank you.
Thank you, Fernando. Any question?
Ricardo, I have a quick question.
Okay, go ahead.
Is this travel ionospheric disturbance related to the disturbance dynamo or prompt penetration electric field?
In fact, this traveling atmospheric disturbance, they can occur in the beginning of when we have a very high polar cap potential drop. You have the heating of the auroral regions due to the disturbance. You can have this kind of phenomena that travels very fast from the poles to the equator in the beginning of the magnetic storm. So this is a phenomena that it can occur. In this case, we suppose that that was the reason for that very high peak in the electron density in the beginning, because you see that was in the very beginning of the storm. It's not a disturbance dynamo, because the disturbance dynamo occurs later in the time. And it takes more time to come from the equator to the low latitudes. That was we have sought for the solution of the problem that we faced.
Okay. Any question? Okay. Thank you again, Dr. Inês. Okay, I think we end the section. I'm so sorry for the time, okay? It's not easy to stop important people to speak. Okay, thank you very much. So, have a good night. Have a good
day. Ricardo, before we close the session, I'd like to thank you the contribution of the Yasunobu Miyoshi, Amitava Kuharai, Babantubi Rabiu, Mensi Vakandon, Manilo Marx, Yosuku Yamazaki, Fábio Egito, Exalta Takahashi, Friederike Lilienthal, Emanuel Carvalho, Paulo Roberto Fagundes, Sharon Vadas, Fernando Bertoni, Fabiano Rodrigues, Marco Mila, Inês Batista, Ricardo Buriti, Lorivaldo Lima, that helped us with this session. And also thank you for the audience to attend this meeting. And the discussion on the upper atmosphere and the ionosphere will continue tomorrow. Tomorrow morning you have a student session, and there is a poster session programming to the afternoon. Okay, thank you, everybody. João, do you have an announcement?
Okay.
Okay, I just would like to thank everyone, the hosters here, the speakers. It was amazing. It was another amazing day here in the ISP. And I also would like to thank the participants for the questions, for the presence. And tomorrow, or for tomorrow, I'm going to send the message for the first speakers of tomorrow morning up to the end of this section, and then we restart at 8 a.m. Tomorrow morning for the last day of ISP 2020. So thank you everybody again, and see you there.
Okay. So